Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We've finally left all the stars behind, and now we're going out and looking at the entire universe as a whole. So this begins the series of lectures on galaxies, the great, the larger universe, and the Big Bang, the origin and fate of the universe. So let's start off with a cosmic address. And first we're going to define what we mean by the concept of cosmology, which is what we're going to be talking about for the next bunch of things. Cosmology is an area of physics, it's an area of astronomy, but it's its own separate thing, and it's the study of the entire universe as a whole. So we're looking at all the physics of the entire universe, how things are distributed on all size scales, how things move about inside the universe, such as galaxies and space and time itself, and how the universe itself evolves with time. And then we're going to be talking about, finally, as we go through this long series of lectures, the age, origin, and fate of the universe. And that's what cosmology is a study of. So most of the things that we're going to be talking about are called Big Bang cosmology, because the Big Bang is the current paradigm for the way we think about how the universe is arranged and how the origin of the universe. And there's four big pieces that are associated with the Big Bang, and I'll start with number 0, which is an underlying assumption. And the underlying assumption to everything is that the universe on the largest size scales is homogeneous and isotropic. And homogeneous means it doesn't matter where you go anywhere in the universe, you're going to have roughly the same stuff around you. And isotropic means that no matter where you go in the universe, you're going to see roughly the same things in every direction. And that's those are two different terms. They have different meanings when you think about it, but we'll talk that in greater depth later. The next thing that is a cornerstone of the Big Bang is the cosmic redshift, which is the fact that all galaxies appear to be rushing away from us. The farther they are, the faster they're rushing away. Next one is the cosmic microwave background, which is a prediction of a hot early universe. And third is the Big Bang nucleosynthesis, where elements are created inside of the earliest moments in the cosmos. And last is galactic evolution, is just seeing how things change. Because if the universe had a birthday, then it was different ago than it is today. And so therefore we should expect to see that if we should have observational results that show us that galaxies actually change with time. And so these four things, with one underlying assumption, give us what we call Big Bang cosmology. All right, so our first important thing that we're going to be looking at that relates to that number 0 is called the cosmological principle, and that there's really nothing special about any place in our location of the universe except for the fact that it's our place and it's our home. That's the only real special thing. And basically, if you went anywhere else in some other galaxy, you might be in where there's many more galaxies or many more stars or something like that. But the underlying idea of the cosmological principle is that the laws of physics are the same everywhere in the entire universe. That's what the cosmological principle really means. So it's a very fascinating assumption, and it's a principle that is borne out by observations. All right. And the cosmological principle implies that isotropy, meaning looking the same in any direction that you look, around any one point in the universe, combined with this cosmological principle, means that it's isotropic everywhere. Isotropic everywhere means homogeneous everywhere. It means it's the same stuff no matter where you go. And so homogeneous everywhere would mean that no matter where you were in the entire universe, you would see roughly what you do no matter where you looked. So we don't live in a special vantage place. We don't live in some place that's over on the left-hand side up against the dance hall where everybody with the wallflowers, and we don't live in big downtown universe where everything was born and goes out from there. No, we live in just a typical downtown sort of uptown sort of rural galaxy somewhere out in space, and we just happen to be where we are. That's it. So that's a cosmological principle. So let's take this idea and give us our cosmic map and see where we actually get from that. And to be completely honest, I ripped this image from Wikipedia, so hey, have a great time. But let's just go take a look. Here's the Earth. The Earth is our starting point, our first starting point in the cosmic address, and the Earth is a planet orbiting the Sun. And yes, the Earth is actually round. Don't worry about those people that say it's not. They're very, very silly. And so the Earth is one of 9 planets. I'm going with 9 because I knew Clyde Tombaugh, who was the discoverer of Pluto, and I'm all about that stuff, and I thought the New Horizons mission was really something. So I'm all about Pluto, so I'm going with 9. But there are lots of other objects that orbit the Sun other than Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. There's a number of dwarf planets. There's zillions of asteroids and comets and things. And the rough size of our solar system diameter is about 50 times the distance between the Earth and the Sun, or 50 astronomical units. And that goes out to roughly what we call the Kuiper Belt. The Kuiper Belt is roughly where most of the short period comets, meaning some comets that are a few hundred years or less in terms of their orbit around the Sun, that's where they come from. And Neptune and Uranus and other large bodies such as Eris and Haumea actually would disturb these things and cause them to fall into our solar system. So that's our first line from Earth to the solar system. And then we zoom in and look at the Sun in the center of this diagram, and we're looking at the nearby stars. One of the nearby stars is Sirius, another is Epsilon Eridani, then Tau Ceti, but the nearest one to our own is Alpha Centauri, actually Proxima Centauri, which we don't see in this diagram because, well, it'll be right next to Alpha Centauri, but just a little bit closer. And it might look like Tau Ceti, or the others are the same thing, but we're trying to pretend like this is a three-dimensional map. So many of these stars that we see here are actually kind of bright ones in our night sky. And our solar system is part of the solar interstellar neighborhood, which spans roughly about 50 light years across, is a big thing. And you see that these dots that are stars, they do not fill this place. They look like fireflies in a jar, and that's a pretty good way of analogizing it. However, the problem with this image is that the stars themselves are extraordinarily tiny with respect to their distances. So if we were being truly honest, we would not have any of these stars bigger than a pixel on this image, and we'd have to really zoom in just to see them. They would just be bright points, not disks like we see. But let's take some liberties and stick with this, because, you know, hey, Wikipedia had its thing. So we'll live with it. That's okay. But what we can see is that the space around us is not densely packed with stars. All right, so our local solar neighborhood is one of many such neighborhoods in the entire Milky Way galaxy. Now, the Milky Way galaxy is about 100,000 light years across and composed of 200 billion plus stars. And so when we zoom out from something 50 light years or 100 light years across to 100,000 or 1,000 times that size, or 10,000 times that size, we see that our Milky Way is a vast collection of such stars, where the spaces between the stars are incredible. But yet, however, when we look at this size scale, it looks like one fuzzy big object, and that fuzziness comes as a result of the smoothing effect of seeing so many things from such a great distance that you can't resolve individual things. So the center of the Milky Way isn't a big ball. It's a huge number of stars, and those stars are actually so dense in that region that from viewed very far away, they merge into one thing. But they're not merging. Remember, the distances between stars are incredibly vast. So this Milky Way is made up of huge numbers of stars and gas and dust. So next we say, let's go out further in our cosmic address, and we see the Milky Way galaxy. We zoomed out much further, and we see there's some other little galaxies around it, such as the Large and Small Magellanic Cloud, some other dwarf galaxies, all these little tiny dwarf galaxies in the local galactic group, which is about 10 million light years in diameter. It's about 3 million light years to the Andromeda galaxy, the nearest large galaxy to our own, with the triangulum, the M33, and their small spiral galaxy close by. But now we're not looking at individual stars, but each of these galaxies, specifically M31 and the Milky Way, are composed of billions of stars, hundreds of billions of stars. And the triangulum galaxy, being a smaller thing, doesn't have as many, but we can see there's incredible gulfs of space between the galaxies. And the Milky Way and Andromeda are falling towards each other and will collide in about 5 billion years or so, long after the sun has burned out. All right, so we zoom out even further and look at the center of this image is the local galactic group, and the local galactic group is a series of galaxies that are part of the Virgo supercluster of galaxies. And so now we see groups of galaxies, many large groups, with the Virgo cluster off to the right, which is composed of thousands of galaxies. The Fornax cluster down in the lower left is also composed of thousands of galaxies. The Virgo cluster is about 65 million light years away from home, and so the light that we see from these distant galaxies left at the time as the dinosaurs were being wiped out by meteorites on Earth. So we're looking at an enormous size scale where the diameter of this area is over 200 million light years, and light takes 200 million years to cross this vast gulf. But notice there's huge amounts of space too. There might be some scattered galaxies throughout, but in general, the spaces in between superclusters, in between clusters, are filled with huge amounts of empty space that we call voids. Now we zoom out even further, and we find the Virgo supercluster is just the spur of another very large supercluster of galaxies. Then the local superclusters can be mapped in this way that goes with a diameter of about 2 billion light years. And these are now superclusters of galaxies, which give us hundreds of billions of galaxies, of galaxies. Of stars, and there is an enormous, vast area. But notice what we're seeing now is it starts to look kind of cloudy. The superclusters themselves group into filaments and sheets and lines, and those filament sheets, lines, and nodes kind of form the edges of a foamy-like structure, which are tendrils connecting together. And the reason for this appearance is a result of what we call dark matter. And these superclusters are the places where most of the matter in the cosmos has fallen together. And we see that there's enormous voids that can span up to 500 million light years across, such as the Boötes void and the Capricornus void and the Sculptor void and the Fornax void, all these other major voids where there simply are no galaxies in anywhere. And if we look at down the Horologium cluster, we see part of another huge supercluster off to the side that leads us to what we call the local superclusters group that we saw in the depth of this, and now we've zoomed out so far that even superclusters themselves look like tiny specks. And so if we imagine a diameter of an area of a volume over 27.5 billion light years in diameter, meaning the light travel time across such a diameter would be 27.5 billion light years. We see that it's now at this size scale, at this distance out, the universe itself looks smooth, meaning we have smoothed it out so that when you take a bucket of the universe, and that bucket of the universe might be, say, 1 billion light years across, now the universe looks really smooth, like the static on an old TV screen that's turned with rabbit ears to some distant, long-lost channel. But this is actually filled with hundreds of billions, if not trillions, of galaxies throughout this observable universe. And it begs the question, what's outside this cylindrical area? And the answer is more galaxies. Because remember, the cosmological principle says it doesn't matter where you are. If we're in the center of this particular group, let's say we go all the way to the edge, all the way to what we would see as the edge. And if we went there, well, we would see exactly the same thing that we see around us now. The same kind of thing. Not the same exact clusters, not the same exact galaxies, not the same exact local groups, but the same kinds of things. Other galaxies, groups of galaxies, clusters, just in a different arrangement with different stars, different pretty things in the night sky for the people that live in that distant galaxy. But they would see the same things in general that we do, up at that edge. So what about the people's edge for that side off to the right? Well, it just keeps going. So we really think that the observable universe, as best we know it, well, the observable universe is what we can see and what we can possibly see. But the extent of the universe, there's a lot of reasons to think that far beyond the observable universe there is a place that is much broader and for all intents and purposes is essentially infinite in extent. So that's our cosmic address, and our grand cosmic map is now what we're going to be talking about, because we started off talking about the solar neighborhood, the distances to stars, and how they live and are died, and how they traverse through the Milky Way and are formed. And now we're going to be talking about the lower levels, and we're talking about how the universe is arranged on the greatest scales of time. Today we're going to be talking about the cosmic distance debate, or more specifically, how we know the distances to the far galaxies. We've been looking at distances to stars using parallax, and now we're going to be looking at the distances to extraordinarily distant objects, the systems of stars like the Milky Way, but much, much, much further. And this debate was one of the most important things that happened in the early 20th century, and we're going to see some of its history, and we're going to see how it resolved. But the real important thing is we look at these stars, we have no idea what their distances are a priori. We just see them as points of light in the sky. And whether or not they were distant objects has been the subject of wonder for thousands of years. And only in the early part of the 20th century did we finally get a glimpse at how far they are. So the distance problem is incredible because getting distances will always be the biggest technical problem in astronomy, and frankly, the most important thing to relate astronomy to astrophysics. Because if you don't have distances, you can't know the luminosity, size, mass, or the distribution space of objects. And without this, you can't understand their lifespans, how they were born, how they live, how they die, what they do, how they evolve, or anything. So distance is the key thing in astronomy, and it's also one of the most difficult things. All right, let's see how difficult. Very early on in previous lectures, we talked about the astronomical unit, and the astronomical unit is incredibly important because it forms the baseline for trigonometric parallax. Copernicus used geometry of the orbits of the planets in order to determine the relative distances between the planets, and that was something that could be done, but it took until radar was invented to really get very solid planetary distances using the speed of light and being able to reflect radar off of objects, such as Venus when it's at quadrature from the Sun, so it has a phase of a quarter phase as we see it, and that allows us to measure the distance to Venus relative to the Sun and give us the astronomical unit by simple ninth grade geometry. And therefore we can use trigonometric parallax, which is the measurement of distant stars. But trigonometric parallax, which is the apparent motion of a foreground star with respect to much more distant stars, as a result of the Earth's orbit around the Sun and the apparent change of that location, has a distance limit. On the ground, the best you're going to get is 1/100th of an arc second, and that's going to be using adaptive optics. But the Hipparchus satellite in 1998 was incredibly good because it got out to about 1,000 parsecs, and that is an important distance measurement because that got the accurate distances to about 100,000 or so stars, roughly in that ballpark. The Gaia satellite, though, greatly improved upon Hipparchus in 2016 with its first data release that got to 1% of 1% of an arc second, which goes out to about 10,000 parsecs and has at least 1 billion stars inside of that area. So the Gaia satellite has radically improved distances using parallax, which means distances are much better known to many more objects, which allows the physics to be better known. All right, so we're going to define a new kind of distance that is secondary to parallax distance, because parallax is the only geometric way of knowing things. It's the only direct measurement of distance, and that's why Gaia was such an important mission. But the luminosity distance is just as important. How you do it is you measure the brightness of some object in some filter, say, and then you have some way of knowing or estimating, guessing, positing, or VGing out of the air the luminosity of the object, and then you solve for its luminosity distance by applying the inverse square law of the brightness. And that's what we see here. D sub L is the luminosity distance equals the known luminosity of an object divided by the brightness that you observe it to be times that 4 pi, and you take the square root. So you have to know the luminosity first. So it helps to actually get the luminosity from, say, a parallax of an object, but that tells you something you need to know, which is the nature of a standard candle. A standard candle is something where you already know the luminosity a priori. And if you do know the luminosity before you take its distance measurement or its brightness measurement, then you have what's called a standard candle. And you can calibrate standard candles in many ways, but I just alluded to it before. Take the luminosities of nearby objects where you can get the parallax, and then you find similar objects using some sort of distance-independent property that they share. Maybe the spectrum, maybe some variability, maybe something, who knows, maybe it's got a smiley face. And you assume that the distant objects have the same luminosity as the nearby objects for which you have the good distances. That's interesting, because the step 2 to step 3 assumes that the laws of physics are the same everywhere, and that's what we're always going to assume, that the laws of physics that are nearby us that we would measure in the laboratory apply to distant stars. So we can use the ideas of physics in order to reach out into the cosmos, because we really can't in any other way. So once we get that calibration set of standard candles, then you can measure them for things that are too far for parallaxes. But the trick is this distance-independent property. And every distance-independent property relies on physics, and so we must assume that the laws of physics are the same there as they are here. And in this little diagram, it shows, well, if you have a candle that's of known brightness, you put it farther away, it looks dimmer. And likewise, another distance-independent property is the physical size of something. So the farther away it is, the smaller it appears. But there's very, very, very few standard yardsticks, but there are a few very critical standard candles. And so one of the more important ones is the spectroscopic parallax, because you can easily get the temperature of a star by either looking at its spectral type or its BV color, its B minus V color, or some other color variation. And if you have a well-calibrated HR diagram, then you simply have to say, oh, I know it's this kind of star because the luminosity class tells me it is a bright giant, so therefore I know the difference that it's an A81 type star, not an A8 main sequence star. It's an A8 bright giant, not a dwarf. Dwarf would be dim, giant would be bright. And so you can then say, I've got the spectral type and luminosity class, and that's for stars, which are incredibly bright objects that you can see from a distance. Likewise, if you calibrate the HR diagram, then you could say using a known HR diagram, such as the Hyades then becomes the basis for all your other HR diagrams. And so the only reason the Pleiades looks different, its main sequence looks dimmer than the Hyades, meaning a V magnitude that is larger, but the same colors for the same stars, is because the Pleiades is farther away, and so the distant, they just are simply fainter and therefore have larger V magnitudes for exactly the same kind of star. So you calibrate all of these things, get distances to Pleiades, get distances to Hyades, and many other things, and the Hyades itself forms the basis for all of this calibration. So it is the most critical of all of the nearby clusters. And we can therefore build the cosmic distance ladder out of extraordinarily nearby objects. So what we have is a power of 10 in distance. Each time we go up 10, the number across the bottom means something's about roughly 10 times more distant than the other in terms of parsecs. And parallaxes get us out to, say, now much further than we had thought. But originally, the parallaxes got us out with Hipparchus only about 100 parsecs or so. But really good parsecs, really good, we're going to need to push this thing, the little purple thing, to the right a bit more, out to number 4, because that's how far we can see now with the parallaxes, up to 10,000 parsecs. So I've got to update this slide. And we can use proper motions of stars in order to get us there, but then we can use parallaxes to get us to distant clusters with main sequence fitting, and that's where spectroscopic parallax work. But the next one we're going to talk about, the RR-Lyrae and Cepheid variables, are incredibly critical because the study of the LMC, or the Large Magellanic Cloud, and then getting the distance to M31 is the subject of our next conversation, which takes us out to a megaparsec, or 10 to the 6th parsecs. So there were no ways to get parallax or proper motion, or even a group of stars that we would call a cluster in M31. So exactly how far is the Andromeda galaxy, M31? You have to use RR-Lyraes and Cepheids to get you there. So let's see how that was done historically. And the details are coming in, because off to the left on this thing with this picture from CTIO, we see the large and small Magellanic clouds in the center of the Milky Way to the right, but the LMC is on the bottom and the SMC is on the top. And those clouds are actually galaxies, and they're orbiting the Milky Way, and that's what we know now, but we didn't know their distances. And what were those objects? And that was the study of the subject that we're about to talk about. All right. So let's take it back in time. The concept of distance and how big the universe is took a big step forward in 1610. So after thousands of years of looking at the stars and simply knowing that they're far, but thinking they were pasted on a celestial sphere, the Starry Messenger was published by Galilei in 1610, and what he showed was that the galaxy itself is a lot of stars. So he took his tiny telescope and looked at the Milky Way, and these drawings that he did of the stars showed many faint stars that he couldn't see by eye. And so if we look at the Milky Way on an extraordinarily dark night where there's no light pollution, which they didn't have in 1610, I mean, it was actually dark sky, unlike today where you can barely count 50 stars. Back in 1610, a night sky in the city was actually dark. And so you could see many, many, many stars. But through the telescope, you could see more. So therefore, he knew that the galaxy, meaning the Milky Way, was just many, many stars that were faint, that just blended together, that could be resolved with a telescope. And that was the first inkling that the Milky Way was much, much, much bigger. In 1750, a theologian named Thomas Wright created a model of the Milky Way based on theological ideas, and his goal was really a wacky concept, but his goals, basically he said, well, the sun is in some grand shell around the center of everything, and so if we looked along the edges of the shell, we'd see more stars, which is similar to what we see in the sky. We see a shell or a ring in the sky. So if we were in the middle of that ring, we would see stars in that ring around us, and it would taper off. But looking above and below that shell, we would see fewer stars. And so his model has, kind of explains the appearance of the sky, but, this was his real model. So he was looking at the concept of the theology behind the starry work, and we were one of many stars inside this grand shell. And so his conceptualization was that somewhere in the center of some grand shell, which we could not perceive, was God. And God looked out at the rest of the stars around him in the firmament, and all of those stars held innumerable planets, and you can kind of see it alluding to it in this thing. And so his concept was theological, and if you go hunt around at Thomas Wright's work, you find some really trippy stuff. And it's always got these little stars with eyes in the center. It's very Illuminati. But anyway, that was 1750. Well, people like William and Caroline Herschel in 1785, they were a brother and sister pair, and William and Caroline Herschel were arguably one of the most important astronomers in history. They decided, after building a 4-foot diameter telescope together, where William ground the mirror while Caroline fed him bananas over the course of many days and kept him going so that he could keep his arms moving so that the glass could take the shape that they wanted. But what they did is eventually, after many, many years of trying to build this telescope, eventually they constructed the whole thing and started looking out into the sky and looked in many, many directions, about 683 directions, with their big scope. And they assumed that all stars had the same brightness. And if you really don't know anything better, you might as well assume that. And so therefore, if stars are at certain brightnesses, and they're all the same brightness, then how far they are is simply their distance, is their brightness, relative brightness. And so this is starting with the concept that we now know is not true, but in 1785 was a good guess, to say that all stars have the same brightness, and then assume that their distance is based on that. So they assumed that all stars were standard candles, which we know they are not, but still 1785. So they did pretty good. And so this gave them the first map of the universe, the first one ever made. And so the sun was off to the side. We can see the effect of the edge of the galaxy in that little dip where the nodules are with these two little arms, like an amoeba shape off to the left. And so we have this enormous, enormous shape that would be maybe called a grindstone, but the sun's not at the center. There seems to be many, many more stars to the left than there are to the right. And to them, this was the map of the universe. Now, there may very well have been things beyond this, but to them, this was it. These were the stars in the sky. So we seem to be one of many in this kind of patch. And then in 1755, which is prior to this, so we're going to bounce around a little bit in time, Immanuel Kant's a philosopher. In 1755, he thought he looked kind of at Thomas Wright's model of a disk and thought, this seems to be about right. And Immanuel Kant said, well, maybe there would be a disc-shaped lens stars, the universe was a disc-shaped lens, a lens-shaped disk, and was rotating about the center. And the sun was not really any special star in there, and all these other nebulae that were being discovered were rotating Milky Ways similar to our own. And what was being discovered was William Parsons, the third Earl of Rosse. And in 1845, about 100 years later, built a big telescope in Parsonstown. This was in the UK, Britain at this point. And he built this enormous telescope called the Parsonstown Leviathan. And he discovered these things called the spiral nebulae. Now, the spiral nebulae looked like disks, but they had some sort of spiral pattern. Some of them looked edge-ons, had dark bands slicing through the middle, but he could not resolve any of them into stars. I mean, his telescope, while enormous, didn't have the resolution that we think of for high-resolution telescopes today. So this was a big deal, and the structure I don't believe stands today, but this enormous telescope could not be pointed very much to the left or right, but it could certainly be pointed up and down. And using this, he visually recorded the appearance of galaxies that he called spiral nebulae, or nebulous cloudy objects in the shape of spirals. All right, Kant's idea about 1755 idea was brought about. Alexander Humboldt looked at Parsons' spiral nebulae and said, "Those are other Milky Ways. They're just made of stars." And so they're very, very, very far away. So he thought those disky sort of things have the same appearance as the Milky Way, but just viewed edge on and far away. So Alexander Humboldt said the Milky Way is an island universe of lots of stars, and there are many, many, many other galaxies out there, and we're just one of them. And this idea dates from 1845. However, a very famous mathematician, Pierre-Simon Laplace, in 1796, prior to that, we're going to be bouncing around in time, of course, posited that the spiral nebulae that were being seen were actually swirling gas clouds that are in the process of forming planets and solar systems. So gas clouds should collapse under gravity, and as they collapse, they'll form disks if they have any rotation, and this is what Laplace posited. And the solar system is in a disk-like shape, and there's numerous examples of gaseous sort of phenomena, and these were seen in telescopes and in the Orion Nebula. And so people could actually say, well, if there's a disk-like shape, and so if there's spiral-like structures, then these must be spiral formations of new solar systems being found. Now, if they're new solar systems and they're nearby, maybe the rotation can be discovered. And Laplace's idea took more of the Herschel's idea to heart and said, the only things we see in the sky are nearby stars and nearby objects, and so the Milky Way is the universe. And so this is the nebular hypothesis for this spiral nebulae. Well, it was not really understood what the heck is which way to go, and until about 1906, Jacobus Kapteyn said, let's actually do something with this. And so he started saying, let's do photographic star counts in many different directions. And so he took Herschel's idea, but then he said, let's photograph stars and measure the apparent magnitude, spectral type, radial velocity, and proper motion of many stars in a bunch of different zones, over 200 zones. And this huge project had lots of different observatories, 40 different locations, and his process was enormous. It took over almost 20 years to complete, approximately 16 years to actually do the whole thing. And in 1922, he published his concept of the map of the cosmos, that the universe or the Milky Way or what have you, the galaxy itself, the sun was not at the center. There were lots of stars. Many of them were very far. And the diameter of this disk-like structure was about 17 kiloparsecs, or 17,000 parsecs, or 34,000 or 40,000 light years, and about 12,000 light years thick. The thing is that his problem is that he did not understand what interstellar reddening was, and he vastly underestimated it. In fact, nobody really had a good handle on it at that time. But there were other things that were being discovered. And we're looking here at a Kepler Space Telescope view of the globular cluster Messier object number 4. And as you can see, some of the stars seem to be blinking on and off. And this is from Hartman and Stanek of Harvard Center for Astrophysics. And this is using the Kepler mission in its K2 mode, as it only has two reaction wheels to help keep it stable, so it can only focus on an area of the sky for a short period of time before it must move on. So one of the objects that Kepler in its K2 mode studied was this globular cluster, and we can see that there are particular kinds of variable stars called RR Lyrae. They literally get brighter and dimmer with time. And you can certainly go take a look at this stuff and look at Kepler K2 data. It's an amazing, amazing idea to go check out. And there's actually a YouTube video that shows this. And just very simple, stars getting brighter and dimmer, and this is a globular cluster. So these RR Lyrae stars have a particular brightness profile and how they get brighter and dimmer. What's the pattern of brightness and dimness? And they're called RR Lyrae. All right, so if we measure the brightness profile, how they get brighter and dimmer with time over RR Lyrae, they have this particular shark tooth pattern where they rise quickly in brightness and dim slowly. And then they rise quickly and dim slowly. And this is characteristic of the type of variability that you find with an RR Lyrae. And why they're called RR Lyrae type stars is because if you find something with this kind of variation, it's called an RR Lyrae star. So we attribute a distance-independent property to the variability. So there's a variability that seems to be characteristic of some class of objects, and we call them RR Lyrae stars. So maybe there's something that we can use with this. All right. In fact, if we look at RR Lyrae itself, this is the data from the American Association of Variable Star Observers, and this data is actually, you can derive it, you can just go to their website and say, please show me the data for this, and download it, and this is in numerous filters, and this has been contributed by many amateur observers as well as professional observers who are showing the brightness variation in different wavelengths, and so that's what the different colors indicate, in different wavelength bands of light. All right. So RR Lyrae stars are actually physically pulsating stars, and they're found in old clusters, such as even in the galactic bulge or in the halo, and these are globular type. They will be found in globular clusters. So these are old stars that are dying, and they physically are getting larger and smaller. And they have this particular pattern that we saw, that shark tooth pattern, and that particular pattern is a distance-independent property. And so maybe there is a relationship between that, and it so turns out that there is. RR Lyrae are roughly vary between like a few hours to maybe a day or so to get brighter and dimmer, and at their brightest point, they are as bright as about 100 times the luminosity of the sun. So all you have to do is find the variability of it and figure out that it is this kind of variable, and it has that particular pattern, and then see what the brightness is that you compare it and say, oh, all of these stars have roughly the same luminosities at the peak, and so it's an RR Lyrae type star, then there we go. So this is a period luminosity relationship for the period of variability for an RR Lyrae to the brightness that it gets at its maximum. And this is an important thing. And so other variable stars were hunted for, and this is incredibly important. So Harlow Shapley utilized this concept for 6 years. to study the distances to the globular clusters. So he was working with them, and he found that using RR Lyraes as a distance indicator, because you could figure out their luminosities, with their luminosity you could get the distance because you could measure the brightness, yada yada. And so he noticed that they were uniformly distributed above and below the Milky Way, concentrated towards the direction of the Sagittarius, and they seemed to be physically, or at least dynamically, oriented towards that as their center. And using that, he said, well, assume that the center of the globular cluster distribution is the center of the Milky Way. And when he made that position, he said, wow, that makes the sun approximately 18 kiloparsecs from the center of the Milky Way. It's really quite distant. But again, he had problems with interstellar reddening. So he overestimated the distance. But still, that gave us a good distance to the center of a distribution of the globular clusters. Now his results, and so if he takes the whole thing into account, it makes the Milky Way look to be about 300,000 light years across, or 100 kiloparsecs across. The sun's about 16 kiloparsecs, or 40,000 light years from the center, or 50,000 light years from the center. He didn't know the full extent of interstellar absorption, so he overestimated distance. It meant everything that he said was bigger was too big and too far. So what is this interstellar reddening that we talk about? Well, we did talk about it previously when we talked about stars and exactly how they make up and interstellar gas. But we know that interstellar space is filled with this dust and gas, and we know that dust absorbs and scatters blue starlight. And so since it does that, it makes distant stars look red and faint, because if it absorbs or emits it, the stars become, or their appearance looks redder because the blue light's been scattered away, leaving the red light. So if you don't really know, if you can't take this well into account, then you're going to say, wow, that thing's really faint, but it's this kind of object, so it's really, really far. So you could, if say the light from RR Lyrae is going through a cloud, like you see in these two images below, then it's going to look fainter. And so you'll think it's farther because you're saying how bright it looks, and you're assuming there's a luminosity period relation, not a brightness period relation. That means that Shapley and Kapteyn thought that everything was much further than it was, because they underestimated the effect of interstellar dust. And so only in 1930, well after this debate was settled, which we'll talk about, we discovered that interstellar dust absorption was extraordinarily significant. And so that is one of the more important elements of 20th century astronomy, is really measuring this stuff. All right, but let's take it back to the 20s. How big is the Milky Way? How distant are these spiral nebulae that the Earl of Rosse discovered, these spiral-shaped nebulae that he saw visually? And there were two competing concepts for what the Milky Way was. One of them was that the universe is the Milky Way, and so the spiral nebulae are just the island universe said that we are one of many islands throughout the entire universe, and our galaxy is just one of many. And so the cosmos is extraordinarily large, and we're just a tiny little thing inside it. That seemed a little difficult for astronomers at that time, and most preferred the nebular hypothesis. And the nebular hypothesis said the spiral nebulae are simply gaseous clouds, and they knew about a lot of gaseous clouds and nebulae of such forth. They just happen to have a spiral shape. And if we have a spiral shape, and they might be forming planets. And so planets did exist around stars, and stars had to come from someplace. And Laplace was right that gas clouds should collapse under gravity and then rotate. And if they rotate, they're going to form a disk. If they form a disk, they might form a spiral. So the nebular hypothesis at that time was the most compelling. However, the island universe one was also compelling because of the physical characteristics of the spiral nebulae. All right, so let's see how this worked. And so we have a number of people at Harvard who were working to classify stars. And Annie Jump Cannon and the rest of the group were busily working on the nature of stars and cataloging stars. And they were the computers at Harvard. And one of them was Henrietta Swan Leavitt. And Henrietta Leavitt was doing some work finding variable stars in the Magellanic Clouds. And by 1912, she found these brighter variables had these longer periods. So she was the one who first discovered the period luminosity relationship of Cepheid variables, a new type of variable star. But at the time, she had no way of actually getting the luminosity calibration, so she didn't do it. But let's call it the Leavitt relationship because that's what they really are. The Cepheids and RR Lyraes do have this brightness that varies regularly with a distinct pattern. And so delta Cepheids and RR Lyraes, she discovered the period was directly related to the brightness, and that was her discovery in 1908 and worked on through 1912. And this was what she was working on when she was studying the Magellanic Clouds to find their distance, because she found these variable stars inside the Magellanic Clouds while she was trying to find their distance. And again, delta Cepheids are similar to RR Lyraes because they're pulsating supergiant stars, not just giant stars, but they're supergiant stars, and they're found in young star clusters. So you might associate them with star-forming regions. And they're really, really, really bright objects, and they are luminosities between 1,000 and 10,000 times that of the sun, but their periods are much longer, between a day and up to like a month or two. And so she discovered that they have a particular profile and that differs from the RR Lyraes, and so you could calibrate the delta Cepheid luminosity period relationship. And they can be distinguished, in fact, individual ones, because of their brightness, can be distinguished out to almost 120 million light years using the Hubble Space Telescope. But the problem is that Cepheid variables are rare. And as rare things, there's very few Cepheids that are nearby, so it's very difficult to get their parallax. But some Gaia data should be able to include them, and that's something, if you go hunting around, you should be able to find. Anyway, and there's also even two different kinds of Cepheids. There's the delta Cepheid and W Virginis stars. So they're both the same kind of thing, but they have slightly different period luminosity diagrams. So you have to be careful with which kind you found. So delta Cepheid, even still, because of their intrinsic luminosity at their maximum, they are incredibly important standard candles. And so we can see that here is some of the images for some of their variability. This is from the Ogle group, and we can see that Leavitt's relationship that she saw was actually in the Large Magellanic Cloud, or MLMC, is that the time between the peaks, the longer the time between the peaks of the variation, the brighter they are at the peak. So this is the relationship that Henrietta Leavitt found, and that was used to try to get the distances to the Large Magellanic Cloud and thus further as well. So we can do an example one where you say, if given a well-calibrated Cepheid relationship, or specifically the Leavitt relation, Leavitt Cepheid period luminosity relationship, if you find one that has 10 days long for how it gets bright and dim, then we know it's about 5,000 times the luminosity of the sun. And that's incredibly important, because now all you have to do is find the periodicity, make sure it's the same kind of character as a Cepheid, not an RR Lyrae, but a Cepheid variable, and then meaning their light curves, how they get brighter and dimmer with time, is different between RR Lyraes and Cepheids. And so you just read it off if you can find one that has a 10-day period. And if we go back to the original HR diagram about the lifespans of stars, we find that Cepheid variables are supergiant stars that tend to be much larger, and young stars, maybe they're O and A and OB and A stars that are in their time of leaving the main sequence or are dying. And so they are horizontal giant branch stars that are their variability comes as a result of physical oscillations of the star actually getting larger and smaller with time. And any star that's inside this instability strip shows some sort of variability, either Cepheid variability or RR Lyrae variability. And these are evolved stars off of the main sequence. Anyway, let's take a step back. Problem was that her boss, Pickering, kept her from following up on the relationship. However, in 1913, just a year later after Leavitt published her ideas, or at least tried to publish them, he calibrated the Cepheid, her relationship, and took some credit. And then said, well, these are Cepheid variables. Oh my goodness, let's do the necessary luminosity calibration. Did so. 1915, Shapley came in and refined the calibration for the globular clusters of RR Lyrae, which allowed him to start his work. So basically, Henrietta Leavitt gave this whole thing its start by discovering them and determining that there is a period luminosity relationship there. Anyway, in 1920, about 5 years after Shapley did his work, the National Academy of Sciences had enough of this stuff, and they decided, let's figure out the size scale of the universe. Let's bring everybody in a room, and we'll have a big fight. And it's called the Curtis-Shapley debate that happened in 1920. So Shapley from Harvard defended his model for the galaxy and the very conventional, based in a lot of well-understood physics, the nebular hypothesis, which said that the Milky Way is the collection of all stars in the universe, and outside of that is a great vast void. And the spiral nebulae are local to the cosmos. However, there was an upstart astronomer named Heber Curtis at the Lick Observatory who defended Kapteyn's model that the universe was very, very large, and entertained the concept that the island universe hypothesis was the right one, meaning that the Milky Way was one of many. And so Shapley utilized physics and the postulate of the formation of planets and stars. And Heber Curtis utilized the idea that the spiral galaxies or the spiral nebulae looked very similar in appearance to our Milky Way, and so like things must be like objects. So the big battleground questions of their debate were: how big is the galaxy? What was more reliable, the star counts, photographic counts, or Shapley's clusters? And furthermore, what is the distance to the Andromeda galaxy? And what's funny is there was an actual a nova event that happened in the Andromeda Nebula, which was called Messier Object 31, and it was still called the Andromeda Nebula. And it was called the largest spiral nebula at the time. And so we look at this thing and we say, well, how far away is it? And there was a nova that was discovered, and that nova had some regular outbursts. And they thought, well, okay, let's see if we can calibrate that and find the distance to that. And finally, what is the motion of the spiral nebulae themselves? Is there a rotation that they're actually rotating? And what are their radial velocities? And which is the more important? All right, here's what Shapley said. Shapley said that the galaxy is about 300,000 light years across, and there was a nova in 1885 that gave a distance because of a luminosity of only 10,000 parsecs. That's smaller than his idea for the size of the galaxy, and so therefore M31 had to be internal. And interestingly enough, Adriaan van Manen discovered a proper rotation for Messier Object 101. That was his observation of the rotation of a galaxy. So he thought it had a very large rotation that was actually discoverable. And Shapley used that and said, well, if M101 were really distant, and for us to actually be able to see that rotation speed, then it would have to be rotating faster than the speed of light. So combining together conventional physics about the formation of stars, or at least of how stars might form and how planets might form, and all sorts of other things, Shapley had some pretty decent arguments for the concept of the nebular hypothesis for the spiral nebulae, and thus the tiny Milky Way with respect to the universe. Curtis, however, said, well, a typical nova in Andromeda gave it a distance of much further. So that's really odd. So the single nova that Shapley was talking about made it close. But if a typical nova was out there, it's very far, and so therefore the distance is about 10 kiloparsecs. And that gave it roughly a size of Kapteyn's Milky Way at that distance, and so therefore it's an external object and really far. He also argued extensively that the Earl of Ross's original dark obscuring bands that he saw with the Leviathan, and we're seeing with subsequent telescopes for a long time, are just simply edge-on spirals, and they're just like you would see in the Milky Way. So the characteristic of the edge-on spirals would be take a spiral galaxy, a spiral nebula, and look at it edge-on, and you've got this disky dark structure, and you've got a line through it, which is exactly the Milky Way. And so they have these so they must be similar objects. And finally, he said, well, the spiral nebulae have really large radial velocities, so they should be able to escape the Milky Way. Problem is there's lots of shoulds in his arguments. Now, there was no winner to the great debate, and that's the problem. And it was basically get everybody in a room and air the grievances. So there was airing of grievances in this debate. Shapley had the more compelling observational evidence because he felt like he did, but the evidence was flawed. So his observational evidence was compelling, given that it was right, but it wasn't right. It was flawed. And Curtis ended up being right, but his observational evidence was weak, as he said, just look at this thing, it's edge on, and if it's edge on, it could be that. Well, lots of things can be edge on, so it just didn't hold water because it wasn't compelling and exclusing. So the observational evidence that Curtis chose did not exclude other ideas. So there were a lot of things with the debate, and so it was still inconclusive, but the big problem was nobody had a good distance to the Andromeda Nebula, and no one could reproduce Feynman's proper motion of M101. Nobody could. Hint, because it's so far away, nobody ever would. So it was a mistaken observation, so darn him. And it didn't take long. 3 years later, Edwin Powell Hubble ends that debate. He used the 100-inch telescope in Mount Wilson in California and looked for Cepheid variables in the Andromeda Nebula. He used Shapley's version of Leavitt's period luminosity relation for the Cepheid variables, and he got a really great distance to the M31 of 300 kiloparsecs, and that's far bigger than the Milky Way, according to Shapley. So no matter what, M31 is outside the Milky Way. And since he discovered that he kept at it, by 1925 he got better data and he got even more Cepheid variables Andromeda. And he found that even a greater distance of 1,000 kiloparsecs. So he thought it was an incredibly distant object, and so therefore it must be much more distant, it's outside our galaxy, and it must be at least as big as the Milky Way. And he ended the distance debate and ushered in a new era. Because it's starting at this time, we now knew that the universe was extraordinarily large and not just the purview of the galaxies. And in fact, this is what Einstein even said when he thought about general relativity. And he thought, wow, if his original work before that, 20 years prior, assumed that the stars were the universe. And now Hubble comes along and says, well, the universe is really much bigger. So the universe grew in size radically. Nobody knew how big it really was. But in 1925, the concept of how big the cosmos was changed forever. And so here's what he looked for. Here are some of the Hubble's actual data. It has a particular appearance to the Cepheid variables in M33 and M31. And here are the ones that he marked down and looked for specific Cepheid variables. And he showed that both these objects could be too far away. All right, and here's one of his photographic plates where he actually marked variable stars. He actually figured out and found that there was a variable star. So here's a really interesting thing. Here's a 1923 photograph that he took from the 100-inch telescope on Mount Wilson. And here's another set of photographs that he took in 1926, or at least they were released in Astrophysical Journal in 1926, where he noted novas and Cepheid variables all throughout the M33, the Triangulum galaxy. And this led him to understand that these things were incredibly distant. In fact, M100, which is another spiral galaxy, also has Cepheid variables in it, and we can see this Hubble Space Telescope observation with the Wide Field Planetary Camera too. And finally, Dave Soderblom of the Space Telescope Science Institute in 2011 published in 2011 his observations of Hubble's exact field. And so he wanted to actually take an image of what Hubble looked at. And so his Hubble Space Telescope images confirmed using the Wide Field Planetary Camera 3 and the UV integrated spectrograph to discover the appearance of the variability of it using the Hubble Space Telescope. So literally, Hubble looks at Hubble's original data and showed the variability of this star that was in Hubble's first diagram in his first discovery image from 1923. And so the light curve of the Cepheid variable star can be seen here, and this is all out of the Hubble site archive from May of 2011. And I'll post the links for this on the YouTube channel. So we can see here's the little stars that show the 4 observations that they got with Hubble time, and if that is the light curve from Hubble's data, then we can see that the brightness closely matches the expected light curve, which is fantastic. Anyway, other galaxies have them, such as M100. And there's an up-close picture of a Cepheid variable in M100, and other Cepheids exist in other spiral galaxies such as NGC 3021. This is another view by Adam Rees, also utilizing it at Johns Hopkins, hunting for Cepheid variables in stars. And his goal was to actually get Cepheid variable distances because he was looking for supernovae in 1995. So you can see that he's looking for another form of standard candle, which is the supernova 1995 AI, which is what he's looking for actually. And that was his goal of trying to, and he had to make, once he found that supernova, he looked distinctly for Cepheid variables inside of that galaxy in order to get conclusive distances to that galaxy so he could calibrate the distance to that using that supernova's light. We'll see that becomes really important later. All right, so in 1936, Edwin Hubble published his book called The Realm of the Nebulae, and it is one of the most important picture books that has been published in astronomy. It showed really a fantastic set of images. He discovered that the spiral nebulae were actually, now we call them spiral galaxies, and the Milky Way is now just the galaxy, and all the spiral nebulae are now called spiral galaxies. And they're just like the Milky Way. Their sizes are about tens of kiloparsecs across. Their distances are megaparsecs, or millions of parsecs. And his research is still basically, he's asked some of the fundamental questions, and they still are, they're still relevant questions today. So if you go and find that picture, it's an amazing thing. I'm sure it's like a few $1,000s on Amazon if you want to get a used copy. In fact, I doubt you can actually buy a copy, and most of them are in research libraries. Now our current view of the Milky Way is that the sun is about 24,000 or 30,000 light years from the center, and the center is in the direction of Sagittarius. The disk is about 30,000 or 100,000 light years across, or 30,000 parsecs across, and it's about 1,000 parsecs thick, or about 3,000 light years thick, where the sun is. And the middle left-hand image comes from the 2-micron all-sky survey, and the other image is an illustration that's been done by the Spitzer Space Telescope group that shows where the sun is and the rough distribution of the galaxy. So this is what we meant by Earl of Ross's idea of what the Milky Way may look like from a distance. And this is a really good detailed image of NGC 891, which shows a dark band of dust going across the center, cutting across it. And so if we got millions of light years away from the Milky Way and looked at it edge on, this is probably what we would see. Something very similar. Dusty band, some sort of bright bulge in the middle, and a halo of stars around it. Some bright pinkish glows from star-forming regions, and bright stars dotting its lanes, which would be O and B type stars. And so we would call NGC 891 is a Milky Way analog, or something that we might think of as the Milky Way. And so we would say that's the galactic center. And so if this is what the Milky Way would be, the sun would be about 8,000 parsecs from the center. The galactic bulge would be that bulge that we call the center, and the disk would be the galactic disk. So this is what the Milky Way might look like from a distance if we were able to get millions of light years away. All right. So Milky Way and Andromeda are spiral galaxies, and that gives us our rough idea. Where do the globular clusters fit in? Well, the globular clusters make up a halo or spheroid of stars and gas, mostly stars, that make up the halo around the center of the Milky Way. And so Shapley's globular clusters are truly centered on the center of the Milky Way, and that's what we know today. And that's our rough picture for it. O and B type stars are in the disk. globular clusters are above and below the disk. There's a huge bulge of stars, a galactic bulge, and the gas and dust is primarily confined to the disk of the Milky Way. We saw pink emission nebulae that are like Orion star-forming regions or Trifid nebula star-forming regions that are in the disk. And so the gas and dust is in the disk, the hot stars are in the disk, star formation is in the disk, and the globular clusters are above and below. And this is kind of our image for the Milky Way that we have today, and this comes from the Space Telescope Science Institute as well as the, NASA JPL. This is Hertz from SSC, and this is part of the Glimpse team from Caltech. Anyway, if the sun is going around at roughly 200 kilometers per second around the orbit, it will take over 226 million years for the solar system to orbit the center of the Milky Way. So when did the dinosaur, if we are at 6 o'clock now on this location here, then the dinosaurs died out. If we're thinking about it as being a clockwise rotation, then if we're at 6 o'clock, the dinosaurs died out about 60 million years ago, and if it takes about 226 million years to go around once, then the dinosaurs died out roughly between 2 o'clock and 3 o'clock on this diagram, which is really interesting. The age of the Earth is only about 4.5 billion years. So 4.5 billion divided by 226 million, so 4 times each one. So you got 4 times 4 to make a billion. So 4 orbits times 4 is 16, 17, 18 orbits. So the sun and the solar system has only orbited the center of the Milky Way 18 times. So I guess it could get drafted by the U.S. Selective Service. But it still isn't old enough to drink. That's another 3 more orbits. That's in 700 million years. Okay. In any event, that's what we call the cosmic distance ladder, and we start from the Earth, where we do radar ranging to get to the various planets, and that's the astronomical unit. We use the stellar parallax to get us out to the stars. Once we calibrate the stellar parallax with spectroscopic parallax, we can look at distant star clusters. We use distant star clusters to get us variable stars. Variable stars get us out to distant galaxies, and that's how we know the distance to the Andromeda galaxy and beyond. And so this is our picture of the local group of galaxies. The Milky Way is one galaxy. The Andromeda galaxy, M31, is another one. They're separated by an enormous, vast gulf of distance of over 3 million light years. And that gulf is enormous. The size of the Milky Way is 100,000 light years across, and so is the Andromeda. The Triangulum galaxy is there. But in between are tiny little dwarf galaxies and vast emptiness of space. And that's what we call the local group of galaxies, this group of galaxies. And that's how we know how far the Andromeda is, by looking for Cepheid variables. And that was the great debate of 1920. And the result of it is that the universe became really quite large. This time we're going to look at the Milky Way's appearance, and the Milky Way is one of the most spectacular sights that you'll ever see in your life. And it's being robbed from us because of the nature of light pollution across the entire world, but it's a part of our human history, and as such, it's something that you need to go out and see if you can sometime in your lifetime. There are too many lights in cities, there's too many lights in towns for you to see the Milky Way in its grand splendor and glory. But if you go to dark places where light is not present, and you can actually experience nighttime as it was meant to be experienced, then you too can see the Milky Way as the ancients did, and as people up until recently as the 1960s, 1970s, and 1980s saw the Milky Way in the sky. But the Milky Way itself is our home galaxy, so let's go see what that is. And this is, of course, a background picture of the Milky Way in the sky. So I was out in Colorado for the recent total solar eclipse in August of 2017. And at a friend's house, I was looking outside of Boulder. I looked out on the porch and I could see the Milky Way, so I took a picture of it. This is a 60-second exposure of the night sky with a standard DSLR camera looking out into space. And we see this cloudy sort of structure, and that's the Milky Way. It's a diffuse band of light that's in the sky that has dark patches all through it, and those are dust and gas. That's dusty lanes inside the Milky Way, but it's that cloudy sort of appearance that's not smoke from a distant fire. This is in the sky. And so this is a slightly different ISO on top of it, and you can see that the appearance of the Milky Way as a cloudy, bright cloud in the sky punctuated by dark bands. And here's another view from Maine some years in 2016 by Tony Scharfman with the AAI group. And you can see there's the glowing band of light in the sky, and that is the Milky Way. And then there's another better view of the center of the Milky Way as seen by another amateur astronomer. And here's a view of the Trifid Nebula and the Lagoon Nebula embedded inside near the center of the Milky Way. And here's a view that was taken by Stan Honda of the Milky Way looking out over the horizon, with some sky glow from distant cities. But there it is. We can see the band of light in the sky that never changes from generation to generation for humans. So this is what Galileo saw in 1610, and this is what you'll see if you go out to someplace extraordinarily dark. So the Milky Way is our home galaxy, and this is a Stan Honda image, of course. And our home galaxy is the place where we are. Now, I'm not talking about the clouds on the horizon or the platform there. I'm talking about the band of light that looks like a diffuse thing that looks like it has smoke in front of it. That's not smoke. That is dust in the Milky Way itself. And there's another view. This was an astronomy picture of the day taken from Australia of the center of the Milky Way on August 23rd, 2010 at Lockhart Gorge in Victoria, Australia. So go look at that astronomy picture of the day image. But what we see is the galaxy itself, where we have a dusty band going across that's hidden in the glow, and stars are embedded all around it, in front and behind it. And there's a brighter area towards what we might call the center of the Milky Way. So the Milky Way is that diffuse band of light that crosses the night sky, and it's been seen for the entire span of all human culture, and only people under the age of 35 today have not seen it. It's amazing. Most people alive today, born within the last 30 years, have not seen it, but every human prior to their birth has. And it's had many names: the celestial river, the celestial road, a path, the backbone of the night. And our words galaxy and Milky Way are derived from Greek and Latin derivations. And galaxius means the milky band, and lactea is milky, and via means road. So Via Lactea is the road of the milk. So a Milky Way or a Milky Band or a Milky Path has been something that's been seen for thousands upon thousands of years, and it was part of our upbringing, it's part of our evolution, and when you actually go and see it, you will be connected to people who were alive thousands of years ago, tens of thousands of years ago, who looked up at the sky and made up stories about the nature of that Milky Way. So what are galaxies? Galaxies themselves are huge assemblies of stars and gas and dust, and they're all held together by gravity. And the largest have about 1 trillion, that's 1,000 billion galaxies or stars or more. And the smallest are really tiny with only tens of millions of stars. And the nearest neighbor to the Milky Way is the Andromeda galaxy, or Messier Object 31. Both our galaxies have about 200 billion stars, for about 400 billion stars between the two galaxies that make up the local group. And this is the Pinwheel Galaxy, or M101, and this is an image taken with the Palomar Digital Sky Survey. All right, so let's take some full sky views of the Milky Way to see what the Milky Way looks like in different wavelengths of light. We started off this entire course looking at different wavelengths and noting that light comes in different wavelengths. So these are both full sky views. One is a full globe image, so I'm kind of trying to allude to the fact that we're looking at the entire sky in the lower right by comparing the same kind of projection that the sphere of the Earth has to the projection of the entire sky. And what we're looking at in the lower right is a full sky image of the entire Milky Way. And the Milky Way has a series of things that are apparent all throughout it. There's dust clouds, there's gas clouds, there's glowing regions, and this is an all-sky image in optical light. So this was assembled as a mosaic of hundreds and hundreds of pictures taken from many observatories all around the world, because the Hubble Space Telescope, even though it takes pictures in optical light, its field of view is far too small in order to create this image. So this was created as a result of a massive mosaic of lots of different observatories that were all over the world in order to make this. And if you look closely at this image, you can see that there's some patchy sort of things when there's slightly different resolutions and slightly different color schemes. But in general, what we see is a dusty band of glowing light that goes across the galactic equator. And so we'll call this the galactic equator. We have a coordinate system centered on the center of the Milky Way. There's stars above and below, and there's a dusty material that kind of permeates the center of it, or the galactic equator. Just down a little bit to the right from the center of the galactic equator, we see the large and small Magellanic Clouds, and way off to the left, just below left, is a tiny little band. That is the Andromeda galaxy over there. And there's pink glows, and those pink glows are star-forming regions, or H2 regions, or regions of the sky where stars are forming, and it's hydrogen gas. So this is the view that we see. Yellowish stars towards the center, bluish stars and pinkish pinkish glows all throughout the edges of this end, and way over on the right-hand side is kind of a C-shaped pinkish glow, and that's the Barnard's Loop around the Orion Nebula. So if we then look at a specific wavelength of light in visible light, H alpha, which is 6563 angstroms, or 6,563 angstroms, we see the glow that's due to hot stars making the light glow. So H alpha is a red wavelength of light, and it is the thing that makes that pink glow that we've seen elsewhere, and it is a place where it is due to hot stars, hot O and B type stars that illuminate this gas, and as it illuminates this gas, it heats up. And as it heats up, it emits in characteristic frequencies of H alpha. So these are star-forming regions in the sky emitting at a specific wavelength that is due to excited neutral hydrogen atoms. And that is the wavelength is called H alpha. Those other dots are point sources. But really, what we're looking at is the bright glows. So where it's brightest is where there's the most hydrogen gas. And way over on the right-hand side, you can see the sea of Barnard's Loop around the Orion Nebula. And away from the galactic plane, notice how the galactic plane is kind of puffy and lumpy with respect to H alpha? There's like bubbles of H alpha. And that's because the gas is being excited by the hot O and B type stars, which excite that gas. All right. So now we shift to much longer wavelengths, and this is a longer wave. This is much longer than the H alpha. It's outside of the optical range. H alpha is still visible light, and you can get that from using filters, but this is an infrared view by, I believe, the Spitzer Space Telescope, and it shows a different view of the sky. We're always going to be doing a galactic equator view, but notice that we have this really tight band with some puffy sort of cloudiness around it, but that tight band is much narrower than the light from the stars that we saw in the original optical. And this is because the infrared view is one of warm dust. So this is much longer wavelength of light, so we're looking at cooler processes, and the cool things that we would look at with infrared would be dust. And so dust is composed of carbon atoms, nitrogen, small molecules that bind together to form larger molecular objects or dusty objects that are no bigger than cigarette smoke motes. So these tiny, tiny, tiny cigarette motes might be thousands of atoms in size at the biggest, but what they do is they can absorb and emit infrared light. And as they do, we find that this dust is confined very tightly to the plane of the Milky Way. And if we look at the infrared camera by the Japanese Space Agency, we see another slightly different version of this with a lot of infrared point sources above and below. But our Milky Way is predominated by this dusty band that glows warmly in the dust, and then away from the center we see it get fluffier. But we could imagine that it's kind of fluffy towards the center, but we just see this large, large thing that might be in the distance. But away from the center of the Milky Way, it becomes fluffier and diffuse as the gas itself becomes more diffuse. All right, another view of the infrared is by the WISE, the Wide Field Infrared Survey Explorer, which is a NASA mission, and it's looking at dust, and the green and red are due to dust, and the light from stars is due to the blue. And the blue-green in the center is due to very, very, very cool stars. And the dusty component is off to the right and left in green. So we see an enormous number of old cool stars as well as dust and gas. So infrared light is dominated by two components. The first is very, very, very tiny M-dwarf type stars, or even smaller dwarf stars, the smallest mass stars. And they're confined to the plane, but you do see some sort of a bulge type thing in the center to elucidate the Milky Way center. But then out away from the center, the light is less dominated by that, and away from the center of the Milky Way, we see only the dusty regions of the green areas. The green area is dominated by dust. So those are the two components that create infrared light. The fluffy, cloudy things are clouds of gas and dust, and the blue elucidates the tiny, tiny, tiny starlight by infrared emitting stars. Now, if we go further and further longer wavelength to 21 centimeter wavelength, which is approximately about 6 inches or 8 inches long wavelength of light, this is due to neutral hydrogen gas that is very, very cold, extraordinarily diffuse, and hardly ever interacts with any other hydrogen gas in its surroundings. It also is confined to the plane of the Milky Way, just in the same way that the dusty structure is and those cool stars are. And so this is a place where where it's not clumped together, not tightly clumped. So this is hydrogen gas that is extremely diffuse and cold, and is due to the electron flipping from one state to another, flipping its orientation of its spin from up to down, and that gives off that long wavelength. This is a radio emission light. And so deep in that radio emission light, we can also look for carbon monoxide, or CO, in microwaves. And microwave frequencies are longer wavelengths of light. And this was seen by this is a map of the carbon monoxide as seen by the European Space Agency's Planck satellite as it's trying to map the cosmos. And one of its important missions is to map what the heck the distribution of microwave emission is due to the galaxy. So we then see that the carbon monoxide is a bright emission towards the center, but it gets very fluffy towards it also has these fluffy high cirrus clouds. So the dust component or gas component can be extremely fluffy, like clouds, and they're called interstellar cirrus clouds for that reason. And these are places where the clouds of gas and dust the clouds of gas congregate. But so we think that if we merge the concept of where the carbon monoxide, or CO, is with the neutral hydrogen, and we say that the CO, the carbon monoxide, which is very, very, very low abundance compared to hydrogen, it's actually clearer to see. Carbon monoxide is much easier to see than neutral hydrogen. However, it's a brighter signal. That's the most important thing. It's a much brighter signal. And carbon monoxide traces the hydrogen. And so where there's carbon monoxide, there's cold hydrogen gas in great abundance as well. And so the all-sky image of Planck spacecraft actually combines multiple bands and frequencies. That's it. That was one of its major goals, because it was looking for the cosmic microwave background. So they're trying to take out the effect of the Milky Way. So they looked in numerous wavelength bands in the microwave emission so that they could remove it to see the background emission. And we can see the definite cloudy sort of interstellar cirrus structure that is made up of the microwave emission of it. And that comes from very, very cold gas that is molecular gas, such as carbon monoxide or methane or ammonia, or other diatomic molecules such as nitrogen and so forth. And these other things, they can emit in microwaves, and the dusty component can actually be very warm. and that also can contribute to microwaves as well. And so the sky as seen by Planck, this is the nine wavelength spans that they view in, and you can see the components of the dust and gas as seen by Planck. Now, if we go much, much longer wavelength light, we see what's called synchrotron radiation. So this is at 408 megahertz, and this is an extraordinarily long exposure, but this is by the Park Observatory, as in conjunction with an Australian observatory as well. So a couple of radio observatories made this map of the synchrotron radiation, which is electrons that are spiraling in the magnetic field of the Milky Way's global magnetic field and traveling at nearly the speed of light. And as it does so, they emit these long wavelengths of light as they spiral in this magnetic field. So the magnetic fields aren't very strong, and the electrons are going extraordinarily fast, so they cover an extraordinary distance as they travel. And we see that the magnetic fields that permeate the galaxy follow the cirrus structure on the outer areas, but there's some interesting stuff happening in the center. Now, if we go instead to much shorter wavelengths, and we go to X-rays, which are much shorter wavelengths than we were just looking at, we see the sky dominated by point sources, and those point sources are either black holes or neutron stars or quasars that are at great distance. But the point sources that we see in the Milky Way, which is again the band across the center, those are going to be neutron stars and black holes along the disk of the Milky Way. Above and below are not those types of objects. It could be, but point sources for X-rays are really tough to know exactly their distances, but there they are. Many of them would be extragalactic in nature, but we can see the galaxies' contribution across the center. And then if we look at the ROSAT survey, we can again see what we saw in the long radio wavelength, which is a kind of strange bubble shape above and below, with some very, very bright X-ray sources. X-rays are very hard to focus, so that's why this image is extremely fuzzy. So you can't focus them very easily, so we get a very unclear and misty view in full sky images of X-rays. But there we see that strange cirrus cloud that we saw in the synchrotron of radio light as well. And if we go even shorter wavelengths, the highest energy wavelengths of light, we see gamma rays. And gamma rays are almost completely confined to the Milky Way center, but we see that there's point sources all throughout the sky in the blue area surrounding. There are some point sources everywhere, but there's some extraordinarily bright gamma ray sources, one from the center of the Milky Way, and 3 from pulsars, which are hyperdense neutron stars that are spinning rapidly, and we see the gamma rays being emitted from them, from the Crab, which is very close by, and Geminga pulsar and the Vela pulsar. And these are from very young young dead stars, meaning they only recently died within the last 1,000 or 10,000 years. And so they're still able to create gamma rays from the extraordinary magnetic fields that they have as they spin down. But the more interesting thing is that blazar that's there. That thing's millions of light years away. It's hundreds of millions of light years away, yet it's one of the brightest sources in the sky. The Vela pulsar, the Geminga pulsar, and the Crab pulsar are all in the Milky Way and quite nearby. Nearby meaning, within a few thousand light years or so. But that blazar is brighter than them, and in fact it's much, much, much further, at hundreds of millions, if not billions of light years away. And that means we're looking straight down the barrel of a jet from a supermassive black hole. As material falls into that black hole, it gets accelerated to nearly the speed of light and creates gamma rays, and those gamma rays are being directed almost completely towards us. And considering there's hundreds of billions of galaxies in the entire cosmos, and we just see this one in gamma rays, that shows you how rare it is to be looking down the barrel of a jet of material coming out of a blazar. And we'll be talking about blazars and active galactic nuclei later. All right, and so if we look, this image was actually created by an amateur astronomer that was looking, by an amateur photographer that was looking at the Fermi data that we were looking at before, reduced it away and found that there's these bubbles. So not only is these bubbles that are surfacing that come up from the radio emission and from the Rosette X-ray emission, but there's these enormous gamma ray emitting bubbles of gas that nobody's really sure exactly what's causing them, but that seem to be centered on the center of the Milky Way. And those gamma ray bubbles are some form of shock-induced material, where as material hits that, it excites as one atom hits another at nearly the speed of light, that excites the material to emit gamma rays. And maybe even, and then as they emit gamma rays, we see them as bubbles, because it's not that there's a gamma ray bubble, it's that there's material that's being shock heated to the point where it does emit gamma rays. So there's some energetic process that's really happening right down there that's due to the center of the Milky Way. All right, so our Milky Way is just one of many spiral galaxies. We see on the upper left the Andromeda galaxy with a galactic bulge. There's a disk and a halo surrounding it. We see M101, the pinwheel, and we see another galaxy, probably NGC 891. And these are the typical types of spiral galaxies, and the Milky Way is one of them. The Andromeda galaxy, M31, is the nearest bright galaxy to us at about 778 parsecs. If you multiply that by 3, about 2.3 million light years away. So all the light that we see coming from there is about 2.25 million years old. And also remember that the disk of this thing is about 100,000 light years across, so the near edge of the disk, the light is actually younger than the far. So we actually have a time limit, a time machine across the galaxy, because the near side of the galaxy is 100,000 light years closer than the far. So we see the far side of the galaxy further back in the past than we see the near side. That's just wild. But what's neat about the Andromeda galaxy is that it's roughly the same type of stars and gas and dust, similar to the Milky Way from internal studies. And we get the rough view of what roughly the Milky Way would look like from the outside viewing in. And this is a picture of, this picture is drawn from Astronomy Picture of the Day on May 10th of 2009. All right, so another view of the Andromeda galaxy is given to us by the Spitzer Infrared Space Telescope, and we see in 24 microns, which is long wavelength infrared, that it kind of has this hot, dusty structure. There's a visible wavelength view that we see to the lower left, but if we compare it to the hot, dusty view, we see that that's predominated by dust and by mostly warm dust, and that's the basic view of Spitzer, is to be a dust viewing object, and also some point sources which would be bright infrared stars. But notice that it's a ring of dusty material that emits in this thing. So it doesn't have a spiral structure so much as a ring structure, which is an interesting way of thinking. But we still think of M31 as a spiral galaxy, even though it's more ring-like in this appearance. In ultraviolet light, the Andromeda galaxy also belies that ring-like structure, and ultraviolet light, such as we see here, the blue light is due to hot O and B type stars, and the longer wavelength ultraviolet light is given in yellow. So the hottest areas are given in blue, and we see that the dusty areas that were given before, that's the place where star formation occurs, and the blue is also ultraviolet, which also traces star formation as well. And the Swift Space Telescope in September 2009 released this incredible study of the Andromeda galaxy, which is an extraordinary high resolution if you go take a look at it, that shows the hottest stars in all of the Andromeda galaxy and where they're forming, so we can see the most active sites of star formation in the Andromeda galaxy is in ultraviolet. And notice we didn't have an ultraviolet all-sky survey. That's because ultraviolet light is very difficult to focus, and so it's much more difficult to create a small telescope that can be put up into orbit for this. And the GALEX probe was the closest one, and we saw that. But GALEX didn't do a full sky survey. It did many, many patches, but nobody's put it together as a full sky yet for whatever they've done. And so if we don't go outside the Milky Way, let's say we got a spaceship and go millions of light years away and look back at the Milky Way, and we look at NGC 891, this is what the Milky Way may look like from a great, 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 great distance. It has a galactic bulge in the center. There's a dusty disk that is very, very tightly confined. And then there's a starry disk that is a little bit broader to that. So the stars are not so tightly confined to the disk, but the dust and all of the star-forming regions, which are those pink clouds that are embedded in it, are. And the galactic halo, which is in the galactic bulge, has a lot of older stars, which would be tiny, tiny stars, but there's so many of them there that they resolve into a cloud of yellow. So the galactic center would be where ancient stars would be, and the Earth from this Milky Way analog. This is what the Milky Way kind of would look like, so we're using it as an example. The Earth would be about 8,000 parsecs from the center. The galactic bulge is where is what we call the central area, and it's mostly red and older stars. And the disk is composed of dust and gas, and we see the pink glow of hydrogen, as well as the dusty material that blocks the light that looks like dark areas, as well as some bright blue spots where young stars are forming. So we can look at another Milky Way analog, which is NGC 7331, which is about 50 million light years away in the constellation Pegasus, and it is a very, very, very distant galaxy. And the little galaxies behind it are even further, about 10 times farther away than this. So we see all these little spiral nebulae around, and if we zoom in and take a very close look at this galaxy, what we see is, ignore the three little galaxies above it, those are much more distant objects, and all the stars that you see in this image, the points and circles, those are a part of the Milky Way. So it's this spiral nebula that we were talking about in previous lectures, this spirally sort of thing, that is what we're talking about, and that's what the Milky Way would look like from a distance. And this object is 50 million light years away, and as such it means its diameter is approximately 100,000 light years across, and it would be composed of hundreds of billions of stars all by itself. And so this is a nebula, not of gas, but of gas and stars and dust. And it's the reason it looks nebulous and cloudy to us is because of its extraordinary distance. But it is composed of individual point sources of stars, hundreds of billions of them. And the gas clouds are emitting light in microwaves and in infrared, and the hot blue areas would be emitting ultraviolet light, and the pink areas would be places where star formation is occurring and is emitting that pink glow of hydrogen alpha that we've seen in the past. And so star forming appears to be happening in these spiral arms, and in the center is where yellow, older, and dead stars are, where there doesn't appear to be much gas and dust. So this is our possible view of the Milky Way if we turned around and went to that galaxy 50 million light years away and turned around and looked back at our Milky Way. We would see something pretty similar to this in the sky. Okay, we're continuing with the Milky Way, and the Milky Way is our big description, so let's start with what we call the Milky Way analog, or something that kind of looks like the Milky Way in the sky. This is NGC 891, a spiral galaxy that has a similar appearance to our Milky Way. So all spiral galaxies in general have a disk in a spheroid structure, and the spheroidal structure starts in the center by the galactic center. There's a disk bulge around it, and then there's a halo of globular clusters around it. And then there's a disk. The disk is as an extended thin disk of stars and gas and dust, and we see the dust in there as this dark band. The gas is illuminated by the red flares that you see in the dust. Those are like Orion nebulas that are glowing because of hot young stars glowing inside of them. And the spiral arms themselves are kind of hard to see in this one simply because, well, it's being seen edge on. But we can posit there's probably something very much like a spiral arm because spiral arms are composed of stars, young stars, and gas and dust. So the spheroid is central, thick and central, and a bunch of stars with almost no gas and dust. So all the gas and dust is way out in the disk. All right. So let's look closely at the disk in the spheroid. The disk in the spheroid, which would be also called the halo, it's an extended group and it's centrally concentrated with almost no gas or dust. And looking specifically at it, when we say that, we're talking specifically about the bulge. And in the bulge, you find a lot of RR Lyrae type stars because those are heavily evolved. stars that tend to be a bit older, meaning they would be G-type stars that were finally evolving into giants. And there'd be clusters of old clusters of stars, such as globular clusters, but almost no gas and dust down in the bulge. All right, but the halo, though, is a much lower density region of the spheroidal component of this. In fact, you don't see it in this image, but they're there. We'd have old metal poor stars, globular clusters, and then there are lyres inside those globulars which help us determine the distance of those things. But in a galaxy of this distance, it's kind of hard to use our lyres in order to get them. In any event, we can detect these globular clusters by looking at deep images that kind of overprocess the galaxy itself. All right, the disk structure itself, though, there's a thick disk of stars, and all spiral galaxies have this thick disk, and it's about 1,000 parsecs thick, or about 3,000 light years thick, and that's composed of stars. And that's young and old stars, and the young stars are in open clusters and loose associations, or we'll call those OB associations with young stars. And then the Cepheid variables appear in young clusters because those are massive stars that are going through their horizontal giant branch phase, which is a very short phase in their life. But they're extraordinarily luminous stars that can be seen. So in any event, we see open clusters and associations of stars inside the disk. The disk structure also has a thin layer of gas and dust. Now the scale height is much shallower than that in the stars. It's about 10 times less thick, maybe only 300 light years thick or 100 parsecs, and it's embedded within the stellar disk. Now what it's composed of is mostly cold atomic hydrogen gas, and that's what we're seeing on the right. On the right-hand side, we're seeing the emission from 21 centimeter radiation, and that's the cold atomic hydrogen gas. That's what's on the right in the reddish sort of diagram. And that happens because the atom that makes up hydrogen has just got a proton and electron, and they both have a spin. And if their spins are parallel, that is a high, and their spin directions are parallel, then they would be, that's in a higher energy state, and the electron can randomly flip so that they're anti-parallel, and all of a sudden that loses a little bit of energy, and it goes to a lower energy configuration, and that emits a 21 centimeter radiation. That's what that glow on the red is about. But on the left-hand side, you have a lot of molecular hydrogen, which barely emits any light at all. So we trace that in the blue on the left with carbon monoxide, and this is a carbon monoxide map made by the Planck probe. And so you can see that this has a completely thinner approach than we looked at with the stars. So gas and dust are the raw materials for star formation, and it comes from an extraordinarily thin area. But as they're formed, they kind of get shredded and puffed, and that's why you see that kind of strange cirrusy-like structure on the left-hand side. So one other possible Milky Way analog is NGC 7331, which is the spirally galaxy in the upper right, not the little neighbors next to it, but what it is. But it's that spirally one left to light. Don't look at the ones down the lower left. That's Stephan's quintet, a group of galaxies. That's very interesting too, but we'll talk about that later. So NGC 7331 is a galaxy that's very similar to our Milky Way, and it's seen nearly edge on and about 49 million light years away. And if you look at the little galaxies above, they're about 10 times smaller, so they're about 10 times further away. They are not part of the system that is this particular galaxy. So if we looked at our Milky Way close up, this is probably what we'd see, with dusty spiral arms punctuated by pink little glows of hydrogen gas clouds that are being illuminated by the stars that are around them. And there's also a certain shape that I want you to kind of look at. If you look really carefully at this thing, you'll see that the dust kind of looks to be on one side of the bluish glows. Now that's interesting. The dust appears to, if we think about it, trail the bluish glows. Now, that's interesting. So it's not that it's trailing the bluish glows. There's something else going on. But let's be that as it may, the dust itself, we're going to get to that pretty soon, but the dust itself is the site is where stars are forming out of, and so is the bluish glow, which comes from the hot young stars that are around. And there's some pinkish type of glows, and those are young star formation regions. All right, so if we look at a Milky Way analog, we see that our sun would be going around a system that's approximately 100,000 light years across, and our sun takes about 2.25 million years to go around the spiral galaxy that is our Milky Way. All right, so I described the spherical and halo components a bit ago, but the main researcher that came out with this was Walter Baade. And Walter Baade was a German astronomer, and because he was a German immigrant in the 40s and 50s, during World War II, he couldn't do anything on the war effort. So he's an astronomer. So he used the 100-inch telescope at Mount Wilson that Hubble had used in order to discover the distance to M31. And he would look at when the Los Angeles lights were blacked out because they thought that the Japanese would come over and bomb Los Angeles and so forth. And so they had blackouts. And because of the citywide blackouts of Los Angeles, that actually allowed them to do this deep sky observation. And at the end of the war, Los Angeles started getting so bright that now the 100-inch telescope, which still exists on Mount Wilson, is completely useless for tasks like this. But at the time, the blackouts allowed him to take some extraordinarily deep images, deep photos of the Andromeda galaxy, of the M31. And what he found was that the disk looks blue, as we saw from the other examples. The spheroid looks kind of reddish, and it has mostly old stars. And he could easily detect individual stars, so that's what he could find with his photographic survey, just like Hubble did. But now Baade made HR diagrams based on the blue and red colors, just like we said, the brightness in the blue minus the brightness in the red, compared to the brightness in, say, the red or the blue, it doesn't matter which one. And those HR diagrams showed that the HR diagrams of the disk were very much like open clusters. And if you took the HR diagrams of the spheroid, they're very much like globular clusters. So he thought that led to the idea that, in general, they were completely different stellar populations. So let's go back and look at that again, because we looked at stellar lifespans a while back, but here we go again. So massive stars live short lives. So if you're a massive main sequence star, you have to be young. They live only a few million years. So if you see an O, B, or A type star, they must be fewer than 100 million years old. The O stars and the B stars are only at tens of millions of years old. But if you find low-mass main sequence stars, they can be either young or old. They can have formed 10 million years ago or 10 billion years ago. Because you really can't tell. Remember, they don't change too much. So HR diagrams of star clusters, if they're young, they have blue main sequence stars. But the old clusters don't have blue main sequence stars. And by old, we mean up to billions of years. So old star clusters can be up to billions of years old, but young star clusters are on the order of tens of millions or at the most 100 million years old. And so Baade took this idea and divided all the stars up in Andromeda into two different populations of stars. So we called one of them Population 1, and those were disk and open cluster stars. And Population 2 were spheroid and globular cluster stars. And the two populations were distinguished by where they were in the galaxies, how old they were, and their chemical composition. All right, so each of those things is pretty important, so let's go through each one. Population 1 type stars are always located in the disk and in open clusters. The ages of the Population 1s can be a mix of young and old, and their compositions are what we call metal-rich. And what we mean by metals, again, is that this is this funny astronomer way of saying there's hydrogen, there's helium, and then there's metals, which is kind of funny, because everything that happens with stars is just basically hydrogen, helium, and that tiny amount of everything else just basically provides electrons to a star and some extra mass and does some strange things down inside. But really what it does is it provides electron opacity for the stellar atmospheres is really what it ends up doing. But in any event, the compositions are metal-rich, meaning they're pretty close to what we find in the sun. And the sun has about 70% hydrogen, about 28% helium, about 2% other stuff. And they're found, then the Population 1 stars are found where there's lots of gas, and they're especially young stars are in that region. So if you find Population 1, you're probably going to find some young stars like some O's and B's there. All right, and they have specific kinds of orbits. Population 1 type stars orbit in the disk, and they orbit in nice ordered patterns and roughly circular things around, and so they kind of do the little blue arrows in the blue disk of this thing, and so that's what we call population 1. They probably have the same orbitals, they orbit roughly in the same general direction, and for a given radius from the center, they roughly go the same speed. So they kind of are pretty regular in that regard. And that's what we would call a semi-relaxed system or an organized system. All right, so then he divided up the second group, which is population 2, and they're located in the spheroid and the bulge. And that's globular clusters and in the spheroid component, and they are extremely ancient stars, and the oldest being up to at least 10 billion years old. And their composition has almost no metals in it. In general, they're at most 1% that of solar, and at the very least 10%, 1/1000th of that of the sun. They have a lot more hydrogen, about 5% more, a lot less helium by comparison, and very little metals. And they're found in places where there isn't any gas and dust, where there is no star formation. So it seems like they were made and nothing else was made next to them, and they are their only generation of their own they self. All right, so the stellar orbits for population 2 are disordered. They're in the halo, they got lots of random orbits, they're either in the bulge, kind of mixed around, doing all sorts of crazy stuff, or they're in the halo just doing their own thing and winging around. They orbit the center of mass just like the disk stars do, but they orbit in incredibly random orbits. Some are going prograde, some are going with the rotation, some are going against, some go up, some go down, some are elliptical, some are circular. It's kind of random. And now if we contrast and compare the two sets of stars, we find that there are two populations that Bada found in our galaxy and in M31. In population 1, they're in the disk, and they're primarily in open clusters. They're young and old stars. They're metal rich, and if there's blue main sequence stars, they're there. They're in ordered circular orbits around in the galactic plane, and they're present with a gas-rich environment, and there's star formation already happening with them. In population 2 stars, however, they're in the spheroid, they're in the halo, they're in the globular clusters, they are the oldest stars, they're extraordinarily metal poor. There's absolutely no blue main sequence stars in their group. It's mostly like G, K, and M type stars, and mostly K and M type stars, and they're random elliptical orbits in all sorts of directions, and they have no dust or gas in there, and they are never coincident with star formation. All right, so what this means is there's a chemical evolution of the entire galaxy. So what is happening is that metals form because metals, astronomy, when I'm talking astrometals, carbon for the purpose of astronomy is a metal. So I really should put that in quotes. So metals form because there's fusion inside of massive stars. So when there's fusion, you get things heavier than hydrogen and helium. And therefore, when there's supernova explosions, they enrich the interstellar medium with the metals that were produced down in the core. And the next generation of stars form with this new gas that's has all sorts of stuff in it, like iron and carbon and oxygen and magnesium and neon and all sorts of other things, phosphorus, you name it. So every successive generation of stars becomes more and more and more enriched with heavier elements, which we call metals. So population 2 stars are an older generation of stars compared to population 1. They were around and they haven't changed since then. So really what we have is that this is an interesting little diagram that was created by the Chandra X-ray Observatory team, and you can think that stars begin on the left-hand side out of clouds of gas and dust. They make protostars, they make stars, they end their lives in either supernovas or planetary nebulae or explode, and the material that has on the right-hand side goes out into the interstellar medium, and you could actually think of it as the right-hand side of this image then loops around to the left-hand side and more protostars are made, and so on and so on and so on. But if you have really young, small mass stars, like the brown dwarfs and red dwarfs, and things less massive than the sun, then they're not going to participate in this because they don't participate, or they're not part of this entire thing. So if they're in a region where there's no gas and no dust and no star formation, then you won't see their buddies or their companions or stars near them getting enriched by the material around them. Now, this asks the question, can a star change its spots? Can a leopard change its spots? So the galaxy as a whole evolves with time, but the chemical evolution affects only populations, broad populations of stars. That's because since fusion occurs deep inside the star, down in the core of the star, and only the carbon, nitrogen, oxygen type elements ever get to the surface because of churning through convection zones, the surface composition, essentially, of a star, the surface composition of the star basically remains unchanged over the star's entire life. Now, since there is some convective churning that can cause some issues that are best dealt with like on a research level, but for our purposes, what we can really say is that the surface composition is essentially unchanged over the star's entire life. You know, there's a lot of course, things that are current areas of research that should go against that, but for an introductory purpose, it's more important to think how we divide things up in simple blocks, and we'll come back at it later if you decide to be a researcher. And once the star forms, therefore, the chemical composition that you have is pretty much fixed for its entire life. So the surface composition that you see on the star gives you a clue about how the star was formed. So if you find that a star has almost no metals in its atmosphere, it probably is a much older generation of stars. And that is borne out by the fact that the chemical composition is different for the spheroid and halo components as opposed to the disk components. And they're completely different that way. So in that regard, we got all sorts of interesting review questions for you to talk about and think about. And what's really I would like to think is that remember that these two groups of stars are really quite divided between what they have, what their chemical composition are, and what their location and where they're found. So that's the most important thing that we're looking at here, is that population 1 and population 2 stars are radically different star groups. They have different origins, and they've been through the cycle. Well, we've been going through the Milky Way and talking about it, and we've gone through a lot of properties of the appearance and the naming of aspects of the Milky Way. But now let's actually look at how the Milky Way evolves and is formed over time. So galaxies have to come from somewhere. And so let's look at what we have on these things. And here's kind of a nice little summary of things that we look at as properties of the Milky Way that must be part of it. And so we can look at remember the Milky Way itself is a spiral galaxy. It's got a disk, it's got a halo, and it's got a galactic bulge. And the disk is really flat. It's got young and old stars. It's gas and dust. There's star formation. Stars are moving in circular orbits and there's spiral arms. And overall, it's got blue spiral arms, and the colors of the stars are kind of whitish because you've got a mix of red and blue type stars. Now in the galactic halo, the halo is pretty spherical. Maybe it might be flattened a little bit just because, pull at the top. There are really only old stars contained in globular clusters, and those are the only things that you have in them. There's literally no dust at all and no gas in the galactic halo. And there has been no star formation during the last 10 billion years, as we've seen from the types of stars that we find in population 1 type stars. Actually, population 2 type stars, none has happened in the last 10 billion years. The stars have all sorts of random orbits in the halo. And there's almost there's no substructure. There's just like globular clusters and maybe some tidal streams and things like that, stars being ripped apart, which we'll talk about in a second. And in general, the halo looks pretty red. The bulge itself is a little different. It's kind of a mix of the halo and the disk. It's pretty flat, but it's flattened along the way of the disk. And it contains both young and old stars, but there's many more old stars. And the more stars, the farther away they are from the center, the more old they are. There's lots of gas and dust, but in the inner regions, but that's only in the central region of the Milky Way, which we'll talk about in the future. And there's ongoing star formation in the inner regions only because there is gas and dust happening. But the star formation is only happening in the very, very central regions of the galactic bulge. However, the stars all have pretty much random orbits in the bulge. but there's a net rotation around the galactic center, and there's always near a ring of gas and dust near the center in the galactic nucleus, which we haven't talked about yet, but we're gonna soon. And the galactic bulge tends to look yellow whitish because of the presence of older stars. All right, so this is kind of our general picture of stars in the picture of the Milky Way. We've got old stars in the halo. Globular clusters are distinctly old. The O and B type stars are only found in the disk. There's emission nebulae, which are those hydrogen gas clouds, which are pinkish. The sun is about 8 kiloparsecs, or about 30,000 light years from the center. The galactic bulge is a mix of old and young, and in the disk there's only young stars, but you can find that there's a lot of old stars too, but you will only find the youngest stars in the disk, in the disk area. And there's the gas and dust is predominantly in the disk. And open clusters are blue and white types things, like the Hyades and the Pleiades, and the double cluster in Hercules. Those things, not in Hercules, in Perseus. That's what's found in the disk. The globular clusters such as M3 and M13, those are found in the halo. All right, so how did the Milky Way form and create this structure? Well, in a very, 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 very general sense, take small bundles of gas and dust in little dwarf galaxies and then smash them together. They have, on average, as they collide and form a larger ball of gas and dust, they will in general have some sort of generic rotation to them. And as they collapse together, they will have there will be some orientation that will have a general rotation to the whole thing that is the average of all of their angular momenta that is averaged over the entire thing. And it will flatten along the axis of that average rotation to make a disk. Once it does so, matter can then, the gas and dust can then fall into the disk, because that's now where most of the matter is. And as then the mass starts to spin up, because material starts to fall into the plane, and eventually you get something where you have a bunch of things that kind of pass through the disk, and those are the old stars in the halo. And the disk then is ordered because that was where the gas came from. So the rotation initially was a big globby sort of spherical thing, but that got flattened, and then the gas kind of just fell straight down, whereas the stars that were formed from the original group were already formed, so they're just going to keep their random motion. So that's what the yellow dots are. The yellow dots are the old stars that were formed before the formation of the galaxy, or during the formation of the galaxy, and before the gas was formed. And in fact, not before the gas was formed, but out of that gas. And the gas that was there was almost all hydrogen and helium. And so those stars were formed out of gas that was only hydrogen and helium. And that's what we mean by metal poor. And so this concept was actually come up with by Laplace in terms of his idea about the formation of the solar system as well as the formation of the galaxy. So we get the disk being a gaseous component because the gas will collapse on the way along the axis of rotation. But the halo, which is stars, won't do that sort of collapse. They'll just kind of randomly buzz around each other, and they will stay buzzing for a very long time. And they've buzzed for billions of years, so they're going to keep going like that. So in general, we take small dwarf galaxies that have very young stars in them, say 10 billion years ago. Over 10 billion years ago, those young stars became the globular clusters that we see in box A. And those globular clusters were made from stars that had almost no dust. They had almost no carbon, no nitrogen, no oxygen, no iron, almost nothing, almost made purely of hydrogen and helium. And so that early generation of stars, that first generation of stars, created the globular clusters, and that's what the yellow dots indicate. And so those stars, some of them were O and B type stars. Of course they were. They died though, and they seeded the first sets of stars that then became the next generation, and that material went out into the gaseous component, which then collapsed along the axis of rotation to keep the gas going. And the gas was not completely used up in the first sets of stars formed as the small dwarf galaxies merged. All right, so that's how the Milky Way was probably formed in the most general sense. And so we still have little galaxies around us, like the Ursa Minor dwarf, the Sextans dwarf, the Carina dwarf, the large and small Magellanic clouds. All these little tiny dwarf galaxies still kind of hover around the Milky Way. And so they're orbiting the Milky Way. They're still there, but they could get absorbed. And in fact, gravity does work. So they orbit, which means they'll eventually lose some of their angular momentum and merge with the Milky Way. But wait a second, there's that Andromeda galaxy thing. It's the same mass roughly as the Milky Way. Maybe it's bigger. And that means that the Milky Way and Andromeda are probably falling towards each other. That's really interesting, but let's talk about that in a little bit. So we can have evidence for this concept of dwarf galaxies getting stripped apart by our galaxy, because there seems to be streams of stars that if we look at certain areas of the sky, we find that there's streams of older population 1 type stars, meaning metal poor population 1 types, or on the metal poor end of population 1. And these are little galaxies that have been tidally stripped apart. And as they get stripped apart, they get stretched into where you can't even see them anymore. And so the Spitzer Space Telescope was able to use infrared view to actually find these stellar streams that orbit our Milky Way. And these stellar streams are thought to be the remnants of dwarf galaxies that have collided with our Milky Way. And in fact, the large and small Magellanic clouds are in the process of merging with the Milky Way, and dynamically they will merge with the Milky Way in the future. And we have evidence for these star streams, and specifically this is an amazing picture from Astronomy Picture of the Day back in 2008, specifically June 19th of 2008, and this comes from Blackbird Observatory by Dr. Gabani, and it also he collaborated with a number of people in order to show the tidal streams around this particular galaxy. These tidal streams demonstrate quite clearly that little dwarf galaxies do get ripped apart by bigger galaxies, and essentially they lose their cohesion because the bigger galaxy simply stretches out these little galaxies, and the stars become streams rather than these clots like little dwarf galaxies or spirals or something like that. And eventually the stellar streams merge with the rest of the galaxy or become part of the halo component of that galaxy. But they don't have enough gravitational influence in order to tear apart the spiral structure of that larger galaxy. So they just kind of orbit in their streams. And so they're kind of like stellar streams that are similar to meteor showers that the Earth encounters as a comet breaks up. They just kind of orbits through the galaxy plane. All right, so we can then we can think that if we look at extremely deep photographic surveys of looking far, far, far away, and therefore far, far, far back in time, we see a gallery of Milky Way-like galaxies from long ago until today. And if we think about the most ancient things, we'd say, well, if we have little tiny dwarf galaxies, those little tiny dwarf galaxies will be very, very blue because, well, they're mostly hydrogen and helium, so they'll be producing lots of blue stars. And that's what we think about with the 11.3 billion years ago. It would be two little galaxies all merging together. So it would be blue, tiny, misshapen, and bright. A billion years later, those things merge together to form something a little bigger. And if another 500 million years later, that'll merge with something else. And then another billion years or so later, that'll merge with more things and acquire more dust and gas. And then another 3 billion years passes and it merges with yet still more. So a continual merger of small dwarf galaxies appears to be the dynamical way that Milky Ways form, like grand spirals form. They keep getting resupplied with more gas and more dust by colliding with more little dwarf galaxies that are primarily gas and dust. So they enrich the spiral structure with more material to create more stars. And so we can see that maybe 3 billion years ago, the Milky Way was a little bit smaller, and another dwarf spiral kind of collided with it to form more Milky Way stars. So this is kind of photographic support for the idea of the formation of the Milky Way by looking at the most ancient galaxies that are very, very deep in space and very, very far back in time, therefore, because it takes time for light to get here from there. So we see things as they were ago if we look farther back in time. And then it really only begs the question, how the heck do we know that it's that far back in time and that far away? And that we'll get to. Have no fear, we will get to that. So what we do is we find that things that are farther away are misshapen, tiny, and bright. And as we get closer and closer, and with almost no spiral structure, and it takes only until later, much later, that you can get a structure that's large enough, that where enough stars have gone through enough generations, you've created enough dust to actually get things that look like dusty bands, such as we see in the lower right image, where there's little dark dusty bands that are just barely visible. And this is a NASA image, and I believe this is a Hubble type image. So yeah, I'll definitely provide the links on the YouTube channel for it. In any event, this is a good little simulation that I think was put together by Dr. Summers at the Space Telescope Science Institute to try to show what would happen as the Milky Way is eventually going to collide with the Andromeda galaxy. So in about 5 billion years from today, the Milky Way and the Andromeda galaxy will collide, they will merge because they're the two big bad boys in the neighborhood, and eventually they will meet and form one big galaxy that we call Milkomeda. Why? Because Milky Way and Andromeda galaxy. So Milkomeda will be the name of the big galaxy. Notice when they merge, the tidal disruption happens and stars are flung out, and the colors go from blue to red. And the reason colors are going from blue to red as the cores merge is that star formation is occurring as the gas clouds merge and do wild outbursts of star formation and get rid of all the gas and form all these stars in massive amounts all at once. And then the spiral structure is destroyed, and you're left with just a bunch of old yellow stars and no gas or dust as it was burned up in a huge event. And that's what's going to happen in about 8 billion years from today. 8 billion. Not in 100 years, not 1,000, not 10,000, not 100,000, not a million, not 10 million, not 100 million, but not even 1 billion. 8 billion years. That's in more time in the future. That's twice as long in the future as the Earth has been alive. All right, so what would it look like from Earth? What would that whole simulation look like? So here's what it looks like if we look towards the Andromeda galaxy today. We see the Milky Way in the foreground is we're pretending the Earth will survive this long, and you can actually set up a camera, and you can pass this down generation upon generation and take the same image over and over. But hey, we're making a simulation here. So this is all simulated at this point. So the Milky Way in the sky, Andromeda there. And then we jump ahead about 2 billion years. The Andromeda galaxy is now so large in the sky that it's something that everybody will always notice and will be part of their lives if there's people on the Earth in 2 billion years from today. Maybe the giant cucarachas that are going to be surviving will enjoy the view. All right, so then we go to about 3.5 billion years. The Andromeda galaxy is now extraordinarily large in the field of view. It takes up about half the sky, more than half the sky in our view. And then approximately very soon thereafter, the stars, because they're starting to collide, there's all sorts of pink star formation regions as stars are formed in furious amounts. There will be supernovae in the sky, tons and tons of super large Orion nebulas and Trifid nebulas. The sky will glow pink at night from the hydrogen glow in the sky, and multiple stars will be going supernova in the night sky. And then if we go And just a little bit further, the star formation continues even more robustly, and large superclusters of stars will occur, and there will be massive amounts of star formation that will disrupt and destroy the remaining gas in the Milky Way Andromeda system, as it's a race between eating up all the gas and expelling it out into space in huge stellar winds that we saw from the Orion Nebula. So massive stars can cause huge stellar winds, which will blow the gas away. And in fact, as these supernova explosions occur, the star formation will dissipate rapidly because the gas is light and doesn't do well against massive shocks. And so maybe in about 4 billion years, as they pass by each other, the Andromeda galaxy will be all tidally stretched. Most of its gas will be used up. It'll all be red stars then. There will be no O and B type stars, but it'll be an interesting and beautiful view. Very strange and red in the sky. And then in about 5 billion years, the core of the Milky Way and Andromeda will appear as a pair of bright lobes in the sky in some direction. That will be just the core remnants of that, and there will be some residual star formation, but really it'll be these two sorts of wild glows in the sky. And then after about 7 billion years, there will be a massive elliptical galaxy. The bright core dominates the night sky. In fact, it might be so bright that there would be absolutely nothing to see at night. There would be very few stars unless both the sun were down and the stars. But in 7 billion years, the sun's not going to even be here. And likely the Earth will be burned to a cinder by the sun becoming a red giant. But hey, maybe this has been taken on one of the distant moons surrounding Saturn that survived the growth of the sun to a red giant. And so this particular sequence was made by the NASA group at Space Telescope Science Institute with LeVay and Van der Merel and Hollis and Mellinger. And they basically put this together to kind of show what the sky would look like from that wonderful, wonderful image that we now know when the Milky Way will collide in about 5 billion years with the Andromeda galaxy. So I have some questions for you to go over and to think about, and we can actually ask what the heck is going on. But we have all this interesting evidence that the Milky Way evolves from an early state from photographic evidence by looking at ancient galaxies deep in the past, that most galaxies were small and blue and misshapen and bright, and then as time progresses, those blue misshapen galaxies that were just deep in the past were mostly made of hydrogen and helium, and then as time progressed, the stars, generation upon generation upon generation, made more and more dusty material like carbon, nitrogen, oxygen, iron, magnesium, and all the other elements that form the dark, dusty bands that would eventually end up to become planets and other stars. So we have kind of a theory about how the Milky Way formed and where it came from. This time we're going to be talking about the Milky Way's spiral arms and how they formed and what they look like. So the most important thing that we have in this section for this time is understanding how we know where they come from and actually how we can measure them, because we see in the past from the previous things that people had thought that the Milky Way was just like the other spiral arms, except we're inside other spiral nebulae or other spiral galaxies, except we're inside it, so we can't see the arms with any great ease. And since the size scale of the Milky Way is so that you have to get over 3,000 light years just to get above the Milky Way, nobody's ever going to do that ever. I mean, ever. Which means that, people don't get these things done. And, humans are not going to travel thousands of light years as an individual and then see them. No, Star Wars movie is just not going to happen in any event. So what we want to do is instead find a way to measure the position and motion of gas clouds, because they trace the size of the Milky Way's spiral form. All right, so again, we know that there must be massive gas clouds and massive dust clouds. We do know that because we see it in the sky. So not just plastered on the side of the sky, we want to see if this cloud is in front of that cloud and in which direction are they, and then hopefully be able to map that. So that's our goal. So what are spiral arms? And spiral arms are these spiral-shaped patterns that are dotted with hot stars, type O and B type stars, young star clusters, and gas and dust. The O and B type stars form in these regions, in the spiral arms, and light them up. And we know that the O and B type stars are very short-lived, so the pattern of the spiral structure should change because, well, they're illuminated by the O and B type stars. So therefore, that pattern must change. And we see giant molecular clouds can be seen in radio light, and the hydrogen gas and dust clouds can be seen in the infrared. But these objects are hardly ever found outside the spiral arms, meaning above and below, or specifically between those things. So the gas clouds must be there, but they get bunched up. So what is all about the bunching? So what are spiral arms? Well, they can't be rotating along with the galaxy or along with the stars, because if the spiral arms themselves were fixed objects and rotated, and the stars played a part in rotating them, then they would stay illuminated, and as such, the things that are illuminated are the stars, and then we would perceive them as spiraling up. So we never see anything like the latter one. There's almost nothing like that in the sky. There are things like the first one in there, and there are things like the middle one, but nothing like the last one. So therefore, spiral arms don't just kind of are formed and are stretched like spaghetti or something like that. That must not be how they work. But we do know that spiral arms are the sites of where massive star formation is occurring. And the sun takes about almost over 200 million years, about 260 million years to take an orbit. And so therefore it'll do a grand total of 50 orbits around the galaxy before it dies and becomes a white dwarf. Now, O and B type stars only live about 1 million years. So 1 million to 10 million years. So let's call it 1 million or 10 million just for fun. And that means they move at most 1 hour on the galactic clock. So you can look at the galaxy as a disk, and we can think that if you move 200 million years or 240 million years in the course of going around once at the radius of the sun, then if that's the case, and let's say an object lives only, say, 2 million years, then that is 1/12 of the orbit. So that's about 1 hour. So we can think of the star moving very short distance on the clock face of the spiral galaxy, very close before they die. So basically where you see an O star is where it was born, is where it's lived, and where it's going to die. And that's pretty much what we think. That's what we know. So we see the O and B type stars and the H2 regions, which they light up, and they're in the spiral arms, and that's what Walter Baade said were the beads on a string. So galactic spiral arms then are probably not fixed objects, but rather density waves, or waves of, or places where there is more stuff. That's a better way of thinking. Waves of stuff where things enter into this traffic jam and then leave. And we can see that from this little diagram that there seems to be a flow because, yes, if you do some Doppler checks and do see the rotation, you do see that the galaxies are rotating. But what exact pieces are rotating? They're not fixed objects. So a galaxy does not rotate as a disk. It is a swirling mass of stars and particles. So what is happening? We can think of notice that the diagram that we see on the left is kind of a quintessential diagram. We've got this dark dust cloud, and in front of the dust cloud, in terms of the rotation, are a bunch of hot O and B type stars. So we can either think of that as being in front of the dust cloud, or more specifically, that's where a lot of stuff is. The spiral arm is where an excess of stuff is, so gas clouds enter the place where there's lots of stuff, get compressed, and then form stars. And then the stars move along from their inherent motion around the galaxy. So it's basically gas goes into the thing and stars come out. That's another way of thinking about it. So spiral arms themselves, if we think of them as density waves, then they can look very similar to this. So everything's got an orbit. The sun's got an orbit. The Orion Nebula's got an orbit. Betelgeuse has got an orbit. Every star in the sky has an orbit around the Milky Way. And because the orbits, every single orbit is an ellipse, that's Kepler's laws, we can then say we can nest the ellipses. So let's say we nest a whole bunch of elliptical orbits and they're offset. Maybe they're rotated a bit and offset by a bit. You'll see that in this nested, rotated version of it all, we find that there's some darker areas where the lines line up. And they tend to be, and when they line up, that's where many orbits cross. And so if there happens to be a star or a gas cloud, specifically let's say a long trail of gas cloud that goes in the entire orbit, so a stream of gas clouds, then as those streams of gas clouds, let's pretend that all of these nested orbits are streams of gas clouds, then they get to a place where they compress together. And so when they press together, there's more gas. If there's more gas, then they can form the stars. So the compression area for the streams of gas is where stuff occurs. All right, so that's what we mean by the nested orbit. And in fact, if you look closely, we can see a spirally sort of pattern. And so if the action is where they get bunched up, then the orbits still are contained with a lot of gas. All these dark lines are where the orbit of the streams of gas are. It's just where all the orbits bunch up is where all the activity is occurring. And that's this idea of a density wave. So we can also think of it this way. This is kind of a little bit of an odd way of thinking about it. There's a kind of a place where things have to compress and get together, and that's just where they're happening. And as they compress together, they have to slow down. And when they do slow down, there's interactions. Or we can say that actually they stay the same speed. Another way to think about it is they're staying all the same speed. They just kind of pass through. All right. So these nested elliptical orbits create the stellar traffic jams. Those stellar traffic jams are where the gas clouds are compressed, and that is about the same. That's exactly how I think. But now if you take this entire system and then rotate it, the entire system then also rotates as a group, and that's because the elliptical orbits aren't fixed. So the entire system rotates, and then you have a rotating spiral galaxy. All right, so again, gas and dust clouds move into those places where the density is higher, and because the gas moves into that place where the density is higher, where there's other gas moving in, then they compress. That forms O and B type stars, and there's remnants of that gas. Then they're illuminated by the hot O and B type stars as they pass through. Star formation occurs vigorously, dust is formed, gas is formed, and you get things like you look off to the right. Now, what exactly kicks it off is not well known. How do you actually start this process? It's an area of active research. But we can see that this explanation has a really good explanation in the terms of the picture to the right, where we see the gas clouds, which are dark gas clouds, which is an overdensity in general. And those are places where the gas is bunching up and potentially beginning the process of star formation. Then that's where we have like the string. So the dark lines are like a string, and the star formations areas are like the beads on a string, such as Walter Baade described. So looking closer at this diagram, we see that the red arrows indicate the gas entering into one of those dense areas. That's where the gas is compressed together. Stars form inside of that. The gas and dust compresses together, forms those stars, and out the other side, because it doesn't stop flowing just because it gets dense. You get O and B type star associations, where there are groups of stars where there's no gas around them anymore, but they're just associated and eventually they explode. And they've used up all their gas. But then you have H2 regions, or ionized hydrogen regions, around O and B type stars if the gas wasn't completely used up in the process. So you get an O and B association if the gas is used up, and the H2 if it's not, and some of the remnant gas somehow made it through. So that's another way of looking at it. And here's a really fantastic example of exactly what I'm talking about, what Walter Baade would do, and this is a Hubble Heritage visual view of the Whirlpool Galaxy M51. So let's see what we mean by the order of things. So we have a general rotation that would be, according to this image, counterclockwise. However, as the gas comes in, it will encounter the density, the dense area of that, the nested elliptical orbits of the streams of gas. And you can almost see how the gas kind of looks nested, and like there's these streams that come into and out of. But yet there's an overall dominant feature that is the dark, dark, dark areas, which are the string-like things which have the beads along them. So two big arms are what we're talking about here, and the gas flows into those dark areas, which is where it's dense, and out the other side flows stars that are brighter. So this is what we mean. We see a dark lane where stars are, where the gas is bunched up, and ahead of that dark lane, after the process has happened, we get the gas compressed, and it becomes these hot stars, and the pink glow is the pink glow of hydrogen. And notice the pink glow of hydrogen and the bright stars are on one side of the spiral arms. That's because the flow goes into the density wave and through the density wave and out the density wave. And notice you don't have too many bright hot stars far from the density wave, because the O and B type stars pretty much detonate before they get a chance to get very far, because they live a very short period of time. So this tells us a lot about the evolution of the stars, and now we're going to then say, well, fine, do we see evidence for that? That's M51, an external galaxy. Do we see it here? And this is an image provided by the Spitzer Space Telescope of a very familiar area of the sky, actually. And this is this is close to the constellation Sagittarius, and M17 is one of the great nebulae, emission nebulae in the sky. But now we're looking at infrared light. And we're actually looking down a cross-section of a spiral arm. So this is like taking one of the spiral arms, cutting it lengthwise, and looking down it. So we'll start off that the flow direction goes right to left in this image, where we have the dark dust clouds that are forming young stars. Then they leave the star-forming region and become an H2 region, such as M17. And that's where we have this bright star-forming nebula where lots of stars are forming, and we got O-type stars that are illuminating the nebula, and the gas has not been used up completely, but it's present in copious quantities around, even to the left and to the right, but M17 is causing it to glow. And then we go further on, and it's older area where there's like a supernova remnant, like kind of a bubble shape where something detonated and formed a bubble. So let's look at each of these areas in turn. Here is a dark dust cloud zone where little tiny stars are being formed. And now, since we're looking in the infrared, we can see through the dark dusty bands and see the young stars that are forming inside of that. So each of these tiny, tiny, tiny dots, and this is from the Spitzer Space Telescope at Caltech, and they call this the dragon and the swan, which is really very elegant. This kind of looks like a little dragon, so go check out their video. It kind of spins a little bit, so that's what I did, is I removed that spinniness, so I didn't like that spin. So anyway, this is their work, and it's an amazing piece of work. Anyways, we see the dark dusty bands, we see the little tiny baby stars. Those are protostars forming inside of the dark area. And then we look to the middle, where we then have a dusty region. Again, there is a lot of dust in this region, and that's what this infrared light is showing. However, it's really hot dust, and this is part of this because it's an H2 region, and this is the Omega Nebula because it kind of looks like an upside-down omega. It's really a tough one to see in this image, but whatever. We see that this dusty region is being caused to glow because of the hot O and B type stars in that area. And then we move over to the left and we see just this kind of faint outline of a bubbly sort of shell. And that has a certain diameter to it, and you have to really kind of squint and stare to see it. But on average, you could imagine that at least there's a cavity that's been formed, and at least there's a shock front on the left-hand side at like 9 o'clock, 12 o'clock, and 7 o'clock. And maybe even there's a kind of a central thing off to the center right where it looks like it's been cleared away. So a shock wave seems to have formed in this area, and that's a natural consequence of a massive explosion of an O-type star. And this would be a very, very, very old thing, and it's sending out shock waves into the cosmos. All right, so that would show the many eras of star formation by looking down a spiral arm, and this work was a result of Povich at Penn State University, utilizing NASA JPL's Spitzer Space Telescope with the IRAC MIPS instrument. So fascinating study of what it looks like down inside a spiral arm. All right, so what's another way that we can see it? Because this is kind of a tricky thing, and infrared light might not be able to give us the map we want. But there is a very good map that we know, which comes from the coldest gas, and that cold gas will show us the source material for stars. So remember, stars are made up of between 70 and 75 and 80% hydrogen. So if we can map that hydrogen, we will map where stars will form from. And if there is no hydrogen, then we shouldn't see any emission. Remember, this is the all-sky image of the Milky Way in 21 centimeters, which is radio light, and it's due to hydrogen emission. And we see it's right along the band of the Milky Way, right down the galactic disk, and we have some high cirrus clouds above and below, but it's concentrated almost exclusively along the galactic equator, and it's very, very, very narrow band. So where does this come from? Well, what happens is you have an electron and a proton, and if their spins are aligned, meaning the proton and electron have a quantum mechanical number or a state that we call spin that is very closely related to angular momentum. And in fact, it is the angular momentum of it. But they don't spin like little tops, but yet they have angular momentum. It's kind of a weird thing. In any event, that's not really what we're talking about, but we'll just pretend for a while that the electron and proton are like little balls and they spin. So if their spins are, and in fact that's not true, but we're just going to pretend for a bit, just for the sake of their argument, and if the electron and proton are spinning in the same direction as the electron orbits the proton in the ground state, this is always, of course, ground state, then it's in a higher energy state, and it can randomly just go, oh, okay, I'm done, and relax and flip randomly. And that will emit light, 21 centimeter wavelength. And it's a 1400 megahertz. So this is definitely down in the radio, and it's a long wavelength, light that needs to be seen with large-scale radio telescopes. And this can only happen when the temperature of the gas is very, very cold, between 15 and 100 degrees Kelvin, meaning just above absolute zero. And the density has to be extraordinarily low, with only 100 to 1,000 of these atoms in a cubic centimeter. By comparison, there's like 10 to trillions upon trillions of trillions of atoms in a cubic centimeter of, say, salt. So these are extraordinarily diffuse clouds, and this is an extremely rare process. So hydrogen makes up most of the galaxy, but yet this is a random process that happens amazingly infrequently. So this will undercount the total amount of hydrogen that's there. So you have to say, well, what's the probability of it happening, and then multiply it up. All right, so this gives us a path, though, because it radiates at a specific wavelength. So our path is look for redshift changes inside the spiral arms. So if you have a small redshift, that means it is, okay, so we have one arm rotating, and some of the rotation of that arm is away from us. So we can think of it as following the blue line, but it's not straight across the blue line. So it's moving both away from us kind of steeply, and it's basically up and to the left, but a nice steep up and to the left. That's arm A. And so that's going to have a big redshift because it's steeply moving away. Now, arm B will have less steep of a redshift, and so it'll be very, very close to whatever it'll have less of a redshift. Arm C, though, is almost completely along the line of sight, so we would expect to have almost no redshift associated with it. And likewise, there can be a blue shift too if it's approaching us. And so we can use this kind of concept to say, where are the spiral arms? And you can say, well, this cloud has high redshift, this cloud has low redshift, this cloud has lots of redshift. And we can then say, that must be approaching us, away from us, and towards us, and we can map the redshift of it, the Doppler shift of the line from that 21 centimeter to say, oh, this is, and map it out in redshift space. So what we get is a picture that looks a lot like this. And this is the picture of the Milky Way in 21 centimeter radiation. And we get the distance to these various clouds by hook and crook with the brightness. So you have a brightness associated with the clouds, and that gives you both the redshift and the 21 centimeter distribution in space. So there is kind of a pancakey sort of structure, and this belies the fact that we see a spirally sort of structure, but mostly we see kind of these ring things. And this is indicative of the fact that these are where the clouds of hydrogen are, and they're not necessarily bound exactly to spiral structure. Remember, they move into and out of spiral structure. So our sun is at the top there, and that kind of wedge at the bottom is because we can't see through the center of the galaxy with 21 centimeter radiation because the center of the galaxy blocks that light. It's so incredibly dense that the 21 centimeter radiation gets absorbed on its way here. So you can see that it was a fascinating little thing that the sun is passing through. That there's like this spur of a spiral arm that we're kind of passing through, and that gives us all the very, very pretty things that we see in the sky, such as the Orion Nebula and all the other star-forming regions that we get to see. And they're not that distant, so we get to see all sorts of pretty stuff. That's what the result of that little hook that goes around us means. Well, a more recent edition of the neutral hydrogen map comes from Levine et al., and they published this in Science magazine in 2006. And they had a much more robust study of neutral hydrogen, and were able to trace out spiral arms. And so their tracing showed that they saw what looks like about 3 or 4 spiral arms, depending on how you map it. So we have these spiral arm structures where the neutral hydrogen map more closely approximates the spiral structure once you get a really good map of where things are. And the sun is, of course, in the central region, right at the tip, right at that kind of wedge. And we're not at the center. The center is the center of the galaxy. All right, so now if we then look out into space and compare this concept, we see that it's very familiar. This is the Triangulum galaxy, a very, very nearby little galaxy, just about the same distance as Andromeda. And M33 has neutral hydrogen. And so the neutral hydrogen, if it's brighter, it's more dense, and the molecular clouds trace that. And those are where the little, so we see that there's all sorts of are tracers. So the molecular clouds can be seen to be tracers of things, and they indicate how many masses of material are in the green dots. So basically, the hydrogen maps out how much hydrogen there is, and so the yellower it is, the more there is. The bluer it is, the less there is. And then there's distinct concentrations in the green dots. So we can then say, wow, this also traces out exactly where carbon monoxide lives. So we can use carbon monoxide as a tracer. We can use H1 radiation as a tracer. And the sources are overlaid. So we have 2 different images with their paper image. So that's a really fascinating study to show that molecular clouds can trace hydrogen. And so then if we really look closely at many things and do an extended survey with say the VLA and through NRAO, the National Radio Astronomy Observatory, and this was the Things survey or the H1 Nearby Galaxy survey. Aren't they great? Aren't they fantastic? So this group led by Walter Brinksblock, by Bijel, Thornley, and Kennicott made a survey of nearby galaxies and looked at their H1, or their neutral hydrogen, in 21 centimeters, and we can definitely see the spiral structures. But there's also some mixy sort of things to them, just like we saw with the Milky Way. So therefore, the Milky Way is definitively a spiral galaxy, just like many of the nearby ones. In the upper left is M101, and that's the Whirlpool galaxy, which is very interesting. Notice that in all of these, the cores, or the very centers, are strongly depleted in neutral hydrogen. The centers are basically excited by things that are happening down in the core. There are some that are actually kind of messed up too, like you can see upper left, right below M101 in the upper left. There's one that kind of looks all squirrely. And basically, spiral structure can be demarked by these neutral hydrogen. And so neutral hydrogen demarks the spiral arms, as well as carbon monoxide emissions. All right, so A lot of little review questions to go over, especially things like how do we know the Milky Way has spiral arms and so forth. And spiral arms are part of it, and we have ways of measuring the size scale of the Milky Way, what its spiral structure looks like. And in fact, infrared maps show this as well, and to some extent. But it's the radio maps at 21 centimeter radiation, as well as Doppler shifts of carbon monoxide and other molecular tracers that show us the spiral arms. This time we're going to continue on our exploration of the Milky Way, and we looked at the rotation of the Milky Way through the spiral arms. We saw that they were made up of stars and dust and gas, but there's something interesting if we study deeper into the nature of the Milky Way. One of the things that you could ask is that how fast is the Milky Way rotating? And that's a really good question. So let's actually begin really far back and go all the way back to Newton and the apple tree and the grand old thing, but let's go way, way back. And remember the old thing where Ptolemy said that the Earth was at the center of the universe? And the Earth was everywhere, and all the stars and those things were orbiting in spheres and so forth. And people eventually discovered that that didn't work. Mr. Galileo came along and showed that Venus had to be orbiting the Sun, and Mars's orbit could only be explained by elliptical orbits. But still, though, Copernicus tried to place things in a new way in 1543, put the Sun at the center, but still kept pretty much everything else the same. He did this posthumously, so he wouldn't be hanged, so that was kind of an important thing. So Copernicus came up with this heliocentric idea mostly because it was just easier to do. And in a certain sense, you got to admire that, but there's no physical reason. There were a lot of arguments against the Earth moving. So Copernicus said this in 1543 with very little justification. Tycho Brahe came along very soon thereafter and also observed that things were a little different, but he created his own version, combining the Earth at the center, but everything else orbiting the Sun. Makes some really interesting orbital paths. Maybe the Sun and Mars could collide, according to this thing, but Tycho Brahe was trying to figure some stuff out. But eventually, Kepler said this does not work, and so as he was using Tycho Brahe's data about the motion of Mars, he found that the only way to make everything work was with ellipses. And so this is what an ellipse is you have the Sun at one of the focal points, say F1, and it rides along this curve that we call an ellipse. And if it's a circle, then the 2 points F1 and F2 are overlapping, and we call it ellipticity of 0. If it's a very large ellipticity, say 0.4, the foci of the ellipse are very spread apart, and the elliptical path of a planet around the Sun is due to just the Sun at one of the foci. And Kepler said this is how it should be in 1609. This was one of his laws. And so then he also determined that when it was close to the Sun, it moved faster than when it was far from the Sun. And that led him, again in 1609, to declare that the period of the orbit of a planet squared is equal to its average distance, A cubed, for all planets orbiting the Sun. And that works really well, where the period is measured in years, and A is the relative distance between the planets compared to the Earth between the Sun. All right. Newton then came along and in 1687 published the Principia, and in the Principia he detailed exactly how motions work and the nature of the laws of motion. And what was derived using his law of gravity is that you can actually really completely derive the law of Kepler's laws in a new way, where we say the period squared, again now, but this time in seconds, is equal to A cubed, where this time A is in, say, meters. And then you have a derivation that's based on the sum of the two masses that are attracting each other due to gravity, M1 and M2. It might be the Sun and the Earth, or the Sun and Jupiter, or what have you. And G is Newton's gravitational constant, and the 4 pi r squared comes about as a result of the geometry of the situation. But in any event, we have G being the link to gravity. Now, if you measure this thing in years, P in years, and A in AU, then strangely enough, because of these solar units, then the 4 pi squared G M1 or M2 becomes 1, especially if you measure M in solar units. So it's very interesting that you can declare that thing to be 1 in the middle. In any event, this is the true derivation of it, and it shows how the orbit of a planet behaves with respect to Newton's laws of gravity. So Newton's laws of gravity were incredibly important, and we don't underestimate them. because they solved a lot of problems that arose from antiquity, meaning how planets move in the sky. They also solved the problems about how everything moves, and we will use this to great effect now. So now let's say we use another one of Newton's important results is that if you have a central force, something pulling, and the thing that is going around in an orbit is on a circular path, it's just the same as you take a string and you put some heavy thing on the end of it, like a rock or a baseball or a weight of some kind, or you go to the gym, you tie your lock on the end of a string and swing it around. People stay away from you, but you can do that. But then the length of the string holding the lock that you're swinging around above your head like some sort of crazy weapon would be r, would be the radius of the swinging of the thing over your head. And then the mass of the thing is the mass of the lock or the object that you have at the end of the string. Say it's a rock. Say you're going to smash the rock with a can of beans or something, or you're trying to open a can of beans with a rock, and so you're swinging the rock overhead, and you're going to smack it on the can of beans to open it because you want beans. So the m would be the mass of the rock at the end of the string, whose length is r, and v is the speed with which it's going around in a circle, and you square that. So if you take the mass of the rock times the speed that's going around in a circle squared divided by the radius of that circle, and there has to be some force pulling on that string in order for it to go around in a circle, and that's any force. It doesn't matter what's doing it. Some force is causing it to go in a circle. Now it could be, let's just pause it for a second, that instead of a string and an arm, that it's actually gravity. And so if it's the gravitational force, and then we equate the gravitational force to the circular force, we derive this very interesting little equation. Well, we derive this thing based on the if we look at energies, we get a factor of 2 in there. But this says if we have a series of things, so that 2 arises because we're looking at the energy of an incredibly large system of objects buzzing around, not just one thing buzzing around in a central force, but a series of objects with total mass m. Buzzing around at some average radius r, and their speeds are indicated by the v squared again. But that too means that you're checking the average over a large set of bodies. But if we're just simply thinking of one thing buzzing around, or one thing in an orbit, you can get rid of that too. And so there's a relationship between the mass that's pulling on something due to the force of gravity and its speed with which it's going around and how far it is going from that center of that gravity. So, just again, we would find that, like Newton's laws dictate, the farther you are away from a given source of mass, let's say all the mass is situated at the center, and g is Newton's gravitational constant, so it doesn't change, and 2 is just some number, which is the average. It says the average. So the speed that you go around, if you're orbiting at far away from the center of mass, the big M, then your speed will drop off as the distance, this 1 over the distance square root. So that's what you'd expect if something is orbiting another large body of objects. Okay, so Newton's discovery and Kepler's discovery originally in 1609, based on Tycho Brahe's data, and then Newton's reforming of his ideas mean that things orbit in near circles around the center of mass of the object. And the farther away you go from the center of mass, all the mass you orbit, the slower you go. So gravity is pulling on things because of the mass. So the gravitational force says every object pulls on every other object, and the mass is the thing that does that. So, and we can also have another very important thing that we're just going to touch on now, is that light interacts with normal matter if it has some sort of electric charge. So if you shake an electron, like we talked about very, very early on, it will emit light. And if you shake a proton, it does the same thing. So also, if electrons and protons can absorb light because they have electric charge, they can also scatter it. So there's interactions that light can have with matter. So if it has mass, it interacts with gravity. If it has charge, it'll interact with light. And we're going to use that now. So one of our big things that we want to talk about, we mentioned that the galaxy is rotating. We talked about that extensively when we talked about spiral arms. So what do you see if you measure the rotation of the disk of the Milky Way using the Doppler effect on the side of the gases? Well, you find that there are motions. You can get the stellar motions from their absorption lines. And ionized gas has distinct emission lines, and those things are from, say, ionized hydrogen or H2 regions. And there's also other gases in there as well, such as ionized oxygen, ionized carbon, specifically oxygen, neon, and carbon. They're pretty good. But in any event, the largest maps that we can get are from neutral atomic hydrogen at 21 centimeters, or H1 regions, or neutral hydrogen atomic neutral hydrogen. And so if this rotating object, the approaching side will be blue shifted and the receding side will be red shifted for a rotating glowing thing that has specific wavelengths of light at which it's emitting. So if it wasn't rotating, it would all be emitting at one wavelength. But because it's rotating, the approaching side will have the glowing portion of the stuff coming towards you will be blue shifted, and the receding portion of the emitting light will be red shifted, so it'll broaden it out. All right. Now, we saw from before that the orbital speed of any object around the Milky Way, and the Milky Way is a vast assembly of stars and gas and dust. But the orbital speed of any object, including the Sun, depends only on the amount of mass that's between it and the galactic center. Now, there are perturbations due to the stuff outside the Sun, but those can be mostly ignored because of the huge amount of mass that's interior to the Sun's orbit. And really, the Sun orbits the galactic center, and the average, and if it was smooth and disk-like, then we can ignore the stuff outside because it averages out. There's a lot of stuff on the far side, but it's far away. There's not as much stuff on the near side, but it's close. So that balances out in this diagram. So we really only care about the stuff inside the orbit, which doesn't balance out. So we can measure what's called the rotation curves. And so we'll plot the speed of the rotation of the Milky Way as a function of distance from the center of the galaxy. And so, interestingly enough, what we're going to find, since it's on a mystery novel, I'll let you know, the disk of the Milky Way rotates about the center of the Milky Way, and it acts as a center. Thank you. Isn't that fun to have that happen while you're in the middle of something? These people are fantastic. So in any event, I'll leave that in just for fun and enjoyment. The disk rotates about the center of the Milky Way galaxy, and the inner parts of the disk rotate as if it's a solid body, but it's not. The Milky Way is not a solid body at all under any circumstances. So what we have is that but then the speed increase for that portion of it, the speed increases with radius, and the period of the orbit is roughly constant because everything is going around at the same rate, like a disk. But the outer parts rotate differentially, meaning as you go further and further out, their orbital speed is about roughly constant. The speed is roughly constant, but the orbital period therefore increases. So one thing lags behind another thing. All right, so this is a graph of what we mean by what we're just describing. In the interior portions, the speed is not constant because it's rotating like a disk. So the outer portions of the inner disk are going faster than the inner portions of the inner disk. So that very, very, very small increase, that steep increase right at the center of the galaxy, at distance roughly close to zero at the center of the galaxy, is very, very tight. But then you'll notice that once we get out to roughly the Sun, it wags up and down a little bit and stays roughly constant all the way out there. This is interesting because notice that little line that says Keplerian motion. We're going to get into what the heck that is. So the outer parts of the speed roughly go about 100 to 200 kilometers per second. The Sun's roughly going about 220 kilometers per second around the Milky Way. But this is interesting. So there's something about those divergent curves on the right that we're going to talk about, which is really fascinating. So what we can do is we can look at this particular graph and determine the mass of the Milky Way, doing all the equations that we looked at before. So once all of the galaxy is within an orbit, the velocity should diminish with distance. So if you see all of the galaxy, or all of the Milky Way is found within one of the orbits, meaning, well, basically everything's inside this orbit and there's nothing outside that orbit, then the velocity should simply drop off because then you're orbiting all the mass. And if you're orbiting all the mass, that's like a planet orbiting the Sun. And if it's like a planet orbiting the Sun, then the farther away you go, the slower you should be orbiting. And that's not what's seen. That's called Keplerian motion. And Keplerian motion is the motion around a body that is very much more massive than the object that's orbiting. Keplerian motion is not seen, meaning it's constant, and in fact it does rise at the edge. So let's look again at this thing. And so a star or gas cloud is held in its orbit by the mass interior to its orbit. That's the real trick there. So the matter outside makes only a small contribution and mostly perturbs the orbit at best. And so we use Newton's law of gravity and the circular orbit to derive the equation below. And notice we got rid of that number 2, and that's because now we're just looking at a single object orbiting a single mass. And that's basically Kepler and Newton coming together for two objects, an object orbiting another object with a circle. And that's what we're saying here. So the mass interior to the orbit, m sub r, is equal to the speed that it's going around the circular orbit squared, times the radius of the orbit divided by Newton's gravitational constant g. So the Keplerian orbit would be what we see on the right-hand side by that equation that we looked at before. If all of the mass of the galaxy were included inside the orbit, then it should drop off as the inverse square root of the radius of the orbit. But it doesn't. So it should fall, but it doesn't. The reason it should fall is because if we're seeing all the mass, if we know about all the mass, then it should drop, but it doesn't. So that's very interesting. But it shows a flat rotation curve out at extraordinarily large radii, like double the distance of the sun from the center of the Milky Way. It keeps going up and up and up. It stays flat. The only way for that to happen is for the amount of mass in the disk to grow at the same rate that the radius grows. So there is just as much mass, there's more mass as you go out further and further and further. And that's the only way for this to occur. So you have to have more mass in order at a given radius. There has to be more and more and more mass in order for the speed to stay constant. That's what this means. So the g is a constant, it's Newton's gravitational constant. 2 is that number that comes from averaging over a large bunch of particles. M is the total mass interior to the orbit, and r is the radius of the orbit. So for v to be constant, the mass must be proportional to the radius. And so if the radius grows, the mass must grow. All right. As an example for the Milky Way, and specifically for the Milky Way, at 8 kiloparsecs hot was where the sun is, the rotational speed is 220 kilometers per second, and the mass interior to it is about 10 billion, or about almost 100 billion solar masses, which is a huge number of solar masses. Now, there are measurements of gas clouds way out in the outer disk, double the distance that the Earth is from the sun, and its speed is actually a little bit higher. It's 275 kilometers per second, and that means the mass interior to it is almost 300 billion solar masses, which is a lot. It's not 10 billion, not 100 billion solar masses, but 300 billion solar masses. So it's a huge amount. 30 billion, actually, I'm sorry, not 10, 30 billion solar masses. Whoops, I'm reading things wrong, aren't I? So it's 30 billion solar masses. 300 billion solar masses. Wow, I really shouldn't have a Montauk beer before I do all these things, shouldn't I? In any event, we measure the rotation speeds in spiral galaxies, and they provide us a great way to measure the masses of these galaxies. The point is you see more mass as you go out, no matter what. All right. So this leads us to the following 3 pictures of the Milky Way. The interior is solid body rotation, meaning, well, the speed is proportional to the distance. Remember, it's not actually a solid body, but when you have a lot of mass packed into a very, very, very small and dense area, it can interact such that it is a solid body. The interior area of the Milky Way is not solid, but it can behave that way. However, we should expect that once you're outside it, you should have Keplerian rotation, meaning you have all the mass interior to it, so it should drop off as inverse of the radius squared. But what's actually observed is the galactic rotation at the bottom, which is the speed is roughly constant. So there is unseen mass. And what do we mean by unseen mass? And let's look very carefully at this, because it's important to actually clarify what we mean and actually prove this with actual data, because that's what we do in science. We actually take data and support our concepts with data, or more specifically, we make a measurement and then try to explain it. And this is the data from Clemens in Astrophysical Journal in 1985. And he made a plot of the rotation curve that's found from carbon monoxide, H2 regions, neutral hydrogen regions, and globular clusters. And we find that much past the 8 kiloparsec radius of the sun, that the data points don't go down. They're scattered, certainly, but they seem, on average, pretty constant as we go out. You have to really average it, and so you smooth it, and it's definitively not dropping to zero. It's certainly not dropping Keplerian-wise. It's certainly going to the right and staying constant, and that's what we mean. This is dark matter. This is evidence for the existence of matter that doesn't do light. And what do we mean by that? Here's a picture of a galaxy that's very similar to the Milky Way. So let's pretend that this is the Milky Way for a second. Stand outside it, and you get about 8 kiloparsecs out, which is about 2/3 the way out. And we find that looking at radio emission from H1 region, neutral hydrogen regions, that it still is spinning much past the bright spots. The bright spots are where stars are lighting up the gas and dust. And they're stars, they're really bright. But then there's neutral hydrogen that's really cold, really dim, and emits only in radio light. So that's what's being measured way out in what looks like the dark region. However, if the stars traced the light, if it was only the stars tracing the light, then you should get the red band. But no matter what, that should be it. However, because it's a constant or staying constant, then the measured speed of things that are far, far, far out there is constant, which means there's more mass that you don't see that's not in the form of hydrogen, which is really interesting. All right, so the average of those three things put together indicates that there must be some sort of unseen mass deep out, way out in there. We start off with a very, very dense region. That's the solid body rotation. That's very dense, close into the core of the galaxy. And then it does try to drop off a little bit, but then there's something else that starts to kick in, and that is the dark matter. Something keeps it from dropping off as Keplerian. There is more mass that is unseen that causes it to spin, to go at the same speed when it should be dropping off. All right. So if we look at other rotation curves of galaxies, not just the Milky Way, we see this to be a very common feature. Each of these graphs comes from Begeman et al. In 1991. There's a number of studies of other rotation curves, and we see that there's three different curves plotted together, and if you add them up, it actually shows you what the component of dark matter should be. The dark matter halo is the dashed dot line, and that dark matter halo is apparently gets larger as it goes further and further out. In fact, what we find is that it's mostly stars and gas and dust in the center, and the luminous components are the dashed components, and the dotted components are dots. So you've got a dash thing, which is like stars, gas, which is the dots, and those things contribute a certain amount of the speed of rotation. But then the full total rotation is the curve going across the top. And that's really interesting that you can separate these things out and find what should be due to the gas, what should be due to the stars. And you have to have some component that's neither gas nor stars in order to replicate the actual data that is discovered by looking at rotation curves of other spiral galaxies. And here's another set. This was by Vera Rubin in 1978, and this was one of the more important areas of her work. And she also labeled the different kinds of spiral galaxies, SA, SB, SCs, and types like that. It doesn't matter the kind of spiral galaxy, they all have these flat rotation curves, which means every spiral galaxy has huge amounts of dark matter. And even if we look at cosmology, meaning the entire universe, we had discovered that roughly of all the entire energy density of the universe, about 23% of the entire energy density of the universe is dark matter. And this can be seen by many, many, many different methods, like say how much mass is there compared to the light. It's a mass to light ratio is what they're measuring. And no matter what, the mass to light ratio says, well, how much mass is there compared to the amount of light there is? And each measurement shows that no matter what, there's a significant amount of dark matter. All right, so what is this dark matter? If it's made of normal stuff, like normal elementary particles that are like protons and neutrons, that would be like brown dwarfs, Jupiter planets, black holes, neutron stars, white dwarfs, primordial black holes, maybe even just puffballs of frozen hydrogen that got stuck out into space. Who even knows? There's lots of things that it could be. But this would just be normal matter. And all of these things would be called massive, compact halo objects, or machos, which is a really fun thing to call them. But massive, compact halo objects are amazing, are an interesting possibility. So let's go look for them. So how would you actually look for them? If a macho passes between the Earth and some distant star, then as it does so, the light that would go in one direction gets bent gravitationally by that object and gets redirected towards you. And so you get what's called gravitational microlensing that briefly magnifies and brightens the star. So you have, the background star. So some dim thing that you cannot see goes in front of a star by pure chance, and it has a perfect alignment so that the light that comes from the far star gets microlensed by the near dark object. And so people went out and hunted for these things and actually found a few. And this is kind of a better view of what it sees. All of a sudden the star gets brighter in the background, and these things have been seen. But the problem is that it takes a huge amount of time, and you have to look at a lot of things because it's extremely rare, because stars are really tiny objects. They might be bright, but they're extremely tiny, and you have to get exactly the perfect lineup to do it. So over 6 years, a particular group looking for machos looked at millions of stars for half a decade, found only about a dozen or so halo microlensing objects by looking directly at the Large Magellanic Cloud or the Small Magellanic Cloud. And worse than that, because you can say, well, it got brighter by this amount, you can measure the mass, and that's a general relativity thing, and that allows you to say that they're small. They're roughly about the size of Jupiter, up to maybe typical white dwarfs. However, you can't make up most of the mass of the galaxy, because if that was making up most of it, then there should be a huge number of these things, but they simply don't occur in huge amounts. So machos cannot be the amount of things, which means that normal baryonic matter is pretty much out. So what do we think they are? And so if you go hunting around and go checking what are the best things they are, and so now you're starting to talk some weirdo talk, right? Okay, what's dark matter? Right now, the wisdom of the internet says, as of summer of 2018, there's basically five top things, and none of them are dark. None of them are normal matter. All of them are like these crazy things. One of them are WIMPs, or weakly interacting massive particles. So these would be normal matter that doesn't interact with light and doesn't interact with the weak nuclear force. They just don't do anything. Kind of like a neutrino, but maybe something else. But nobody knows really what they are. So what are they? They're WIMPs. Nobody knows. And next, well, axions. Axions are even more fun to talk about, because quantum mechanics has some very strange things with respect to quarks, because exactly how do quarks come together to form protons and neutrons? And so a theoretical particle is devised, created, made up out of thin air in order to solve an unsolved problem concerning quarks. So maybe axions exist, and that's kind of like, well, we don't know, but something's got to keep them protons together and them quarks together. And in threes, that's kind of what quarks do. So what's an axion? Well, it's helpful for that thing, but so let's go hunt for it. Maybe it's dark matter. Ooh. So people are hunting for axions. Next is ultralight scalar dark matter, which is a really weird thing. This would be similar to axions, except their mass is so incredibly tiny, so insanely tiny, that their de Broglie wavelength would be thousands of light years long. And then you have another thing, which is like we know of three versions of neutrinos, and we talked about the sun. There were neutrinos coming in the sun and exploding supernovae. That neutrinos come out of the sun rapidly, and they're produced by nuclear reactions, and as they travel through space, they oscillate between the three different flavors. Maybe there's more flavors. maybe there's more flavors. Maybe there's an alternate group of neutrinos that are much more massive than the normal triple of neutrinos, and they only would interact with matter when they flip between flavors and not while they're actually a particular kind of sterile neutrino. So you might have sterile neutrino, big bear, little bear, and mama bear, papa bear, and baby bear, right? Whatever they are. They don't interact with anything until they wonder where the porridge is, and then they interact like crazy. So sterile neutrinos. Then you have self-interacting dark matter, and currently that is the most attractive thing to researchers now, meaning take all the normal matter that we have in the universe and make it dark matter, and you have lots of different dark matter particles. They just simply don't interact with any normal matter except through gravity. And so that's kind of like the Star Trek mirror world, but with dark matter. It's kind of a strange thing. All of this stuff is extraordinarily speculative, and this is a result of the fact that dark matter is an observational thing, and so many ad hoc explanations are created in order to explain something that is that is absolutely necessitated because of that. Many people like to say, well, let's modify Newton's law of gravity because that's a lot simpler than trying to find things that just sound weird, because a lot of people look at this and go, this is garbage. Let's just modify gravity. It'll be easier. Make a new equation. But there's a lot of things that say that modified theories of Newtonian gravity don't work. In fact, there's a lot of predictions of modified MOND things that do not work. So that's kind of out, and that's very much on the downside. It was pretty popular about a decade ago, but not anymore. All right, so dark matter halos. What is the source of this extra mass? If it's not stars and not gas, the galaxies have these extraordinary extended halos. They might contain up to 90% of the galaxy's map, and they're even more extended than the starlight component. They may even go way out to 200 kiloparsecs or greater. So these incredible halos of dark matter surround individual galaxies. And the dark matter, just because it doesn't interact with anything, can't collapse. It can't lose its energy and fall under the influence of gravity. So since it's hot in a way, it must stay hot. And by hot, I mean has big orbits where it's moving fast and can't collapse down into groups. So light and normal matter can emit its energy and collapse and fall into structures like galaxies, but dark matter cannot, so it stays extended. So we find that the Caltech astronomer Fritz Zwicky in 1933 also went and looked at clusters of galaxies, and he found that they were moving extraordinarily fast, maybe thousands of kilometers per second relative to the cluster center. And that's much greater than the escape velocity if you added up all the stars and all the clusters of the galaxies and just looked at the clusters. And he said there must be some component of dark matter, and in fact Fritz Zwicky was the one who created the thing. He called it dark matter, but actually in German it is dunkles Materie, and that's kind of a great thing to say. So there must be the extra gravity, and therefore if in galaxy clusters there must be almost 100% of it is dark matter, which is really amazing. Okay, so we do know, however, that about 10 million, there's this enormous amount of X-ray emitting gas in galaxy clusters, and in fact, this gas is so hot that it's moving so quickly that without dark matter, the gas would dissipate extraordinarily quickly, and we can see the evidence for this dark matter because of gravitational lensing of background galaxies by the clusters. So this, with galaxy rotation curves, means there's a huge amount that we do not see. So let's look at that X-ray emitting gas, and here is something from the Chandra X-ray Observatory. On the right is an optical image of the Perseus cluster of galaxies from the Blackbird Observatory. On the left is a Chandra observation of the Chandra X-ray Observatory observation of the Perseus cluster core, and we see this enormous amount of X-ray emission on the left, which is the center of that. Now that's a huge amount of gas. In fact, it composes more of the hydrogen than all of the galaxies combined. But even still, it's too hot and moves too fast for it to actually stay in this group. It's moving too hot for its light level of mass, or it's not massive enough in order to hold itself together, so therefore there must be dark matter. And then we go to look at galaxy clusters and gravitational lensing. And if you look closely at these images, you'll see these arcs, these arc-like structures. And these arc-like structures are formed as a result of the gravitational lensing by the dark mass as the light from distant galaxies passes through the gravitational field of the cluster of galaxies. And this is galaxy cluster Abell A1689, and it was taken with the Hubble Space Telescope advanced camera for surveys. And there's a Chandra X-ray Observatory version looking at Abell 383, another galaxy cluster, and we can even see X-ray versions of these things. So the purple glow is the outline of X-ray emission. So we have an X-ray emission on top of what appears to be an image taken by not an X-ray. The purple glow is the X-ray, and the starry sorts of images that the galaxy sort of images is from the Palomar Digital Sky Survey of the rest of it. So there's an enormous amount of hot intercluster gas, but it is too hot and is not enough mass to stay together at its temperature. And it's not enough mass there to hold the galaxies in place either. And this is called the El Gordo, which is another X-ray emitting galaxy cluster, and we have other galaxy emitting clusters as G351.03. Well, very interesting names in X-ray. But we also think that much of the gas is primordial, means it dates from the early days of the universe, 13.6 billion years ago, 13.4 billion years ago. But there's not enough in it to become from the galaxy clusters themselves. So how do we know? So can we map this in any way? And yes, we can. And here's how we do it. When you go to see an eye doctor, say an ophthalmologist or even an optometrist, and you want to get new glasses, what they do is they put a series of lenses and they make images and they look at images on the surface of your retina, and they focus images on your retina, or basically specifically focus their view of your retina on their view, and they're really close up too because they want to see what that image will look like. So they want to measure the distortion that's caused by your lenses of your eye. So what you can do is do that in reverse. And by the simple process of, an optometrist would say, oh, so we have a distortion of the background galaxies. They're distorted into little arcs. So what do you have to have in order to distort them? So what is the shape of the lens, meaning you've got something that's causing a change in the lens. And so you can think of this as a gravitational lens. And in fact, we think of ray tracing, and we can trace the light back to its source. And then we ascribe a certain amount of gravitational pull to that, which demands a map of a dark matter. So this purple glow here is now no longer the map due to X-rays that Chandra saw, but rather a derived map based upon the appearance of the cluster, how fast the galaxies are moving, and the gravitational lensing that's embedded inside, that surrounds and embeds the entire cluster itself. So this is an enormously rich galaxy cluster, as you can see, Abell 1689, which is this huge group of galaxies. Our Milky Way is not even close to such a group. It would be we'd have a very different view of the night sky if we were. But in any event, all these galaxies are in this big group, and something's holding them together, and that something is a huge amount of dark matter, and that dark matter is shown in purple, but it's derived through computer simulations, and then the derivation of that computer simulation is overlaid on top of this Hubble Space Telescope image. That's the same for this image, which is the classic bullet cluster. And what we're going to have is that it's three separate images overlaid. We have one which is a visible image, which is the kind of the stars and galaxies sort of image. Then we have the red image, and that's the Chandra X-ray Observatory, which shows where the hot X-ray gas is. And then we have the dark matter map, which is the blue. So the X-ray gas, when these two clusters of galaxies passed through each other, the X-ray gas interacted because it's distributed widely. And it got hotter and formed into these funny bullet shapes. But the dark matter doesn't interact with anything, so it keeps the galaxy clusters together even as the galaxy clusters pass through. So the X-ray gas gets left behind, and then the clusters move on without the X-ray gas. And here's a better picture of that version. So once again, this is a visible light image, overlaid with the red X-ray Chandra image, which shows where the X-ray emission of the ultra-hot intercluster gas is, and then the bluish stuff is the derived map of where the dark matter must be such that the galaxy clusters stay together as they passed through each other. And this is a similar situation to the musket ball cluster, where the red is again the X-ray emitting gas, and we see a series of galaxy clusters, and it's called the musket ball because there's a series of, well, there's a series of ball-like structures, and I guess that works for anybody. And we see where the gas has been left behind as the two galaxy clusters have collided and moved on. And we have another one where the dark matter is mapped in blue, the X-ray emission is mapped in red, and it's similar to the bullet cluster, but it's now been mixed a little bit as the two clusters have moved on to the right and to the left as they passed through each other billions of years ago, or it took billions of years for them to cross that vast gulf of space. And the galaxy and the dark matter just keeps them together. They're not mixing. But the intercluster gas is left behind because it interacts with itself and self-gravitates and collides, just like any gas cloud would. So the gravitational lensing occurs all over the place, and we can see that this gravitational lensing also provides another indirect measure. And here's examples of gravitational lensing here and here with very high redshift galaxies. And in fact, we see them in many different things. And here's an extraordinarily striking view of a galaxy cluster, where we see lensed galaxies deep in the distance that look like arcs. And that is one of the more amazing appearances. We've kind of gone over this a couple of times, but this is Abell 1689 once again, and let's kind of zoom in on a few of them. And the part of the reason for showing these images is that, wow, you don't get to see these things very often, I'm sure. And this is part of the reason, is that these images need to be more publicly seen. And I like this one a lot, Galaxy Cluster Abell 370. Almost everything in the fuzzy objects are all galaxies. But off to the right, in the upper right, is a highly distorted galaxy image. And that galaxy image is projected across the sky in two different locations. And we see that the upper left and the upper left and the lower right are the same exact galaxy, but across the galaxy. And in fact, we see the upper left is, to me, the most interesting of the bunch, because the image of the galaxy, which is behind all of the other cluster galaxies, the light from that distant galaxy, which is very, very bright, got redirected to our eyes perfectly by it's such that well, not perfectly, because it got all smeared out and everything. So we have multiple images of that distant galaxy being smeared out by the foreground galaxy. And here it is, the last one away. And this is a Abell 370 so this galaxy cluster is about 5 billion light years away. And we're looking at something extraordinarily distant that is much farther away than the galaxy cluster. This is kind of off to the side of the galaxy cluster, this image. But the smeary tadpole thing is much further than the galaxy cluster. It might be 5 or 10 billion light years even further away, which means we're looking at something that's very, very distant. If it's 10 billion light years away, then we're seeing something that's 5 billion years older than all of the other, or 5 billion years younger than all of the cluster, the galaxies in the cluster that are in the foreground. And we can see some evidence for the earliest nature of a galaxy in this thing, that they're very strange and small and bright along their lines. And we see huge, bright, starry features in this galaxy. But it has multiple images, and they've all smeared around into this tadpole shape due to the distribution of dark matter in the galaxy cluster that alters the path of the light. All right, so that's an enormous, enormous overview of the nature of dark matter in our Milky Way and beyond. And I could have left a lot of that stuff for much later in the course, but I figured dark matter is such a really interesting topic. I'd take some extra time with it, and as a result, I have a lot more review questions for you to go over and take a look at. There's a whole bunch, but you can do them as you want. But what we really think is that dark matter actually does exist. And the hard part about dark matter is that all of the things that might make up dark matter are very strange sorts of things. They aren't normal matter in any sense of the word. They can't be necessary. Most of the matter can't be normal atoms or molecules or planets or white dwarfs or anything, because they're just not numerous enough. And people have been looking for them. So they must be some strange, weird subatomic particle predicted by the standard model or the extended model of particle physics. They might be there to solve some crazy problem in quantum mechanics or something. And so there are a number of active searches for dark matter candidates, and I'll post some of those links on the YouTube channel, the links below. So we really do think that most of the matter in the universe is actually dark matter and not normal matter. That's the real trick with this. So we're going to see what that means when we get to cosmology. We're continuing along with the Milky Way for our final bit about the nature of the Milky Way itself, but we're going to start by looking first at the Andromeda galaxy, which is the nearest bright, large galaxy to the Milky Way. And let's say we take an optical view, such as we see on the left of the entire Andromeda galaxy, and focus instead just on the central regions, and we look in the X-ray areas. So we're using the Chandra X-ray Observatory. And if we zoom in, looking with a combined X-ray and optical view of the center, we find that the blue glow, which is due to X-ray emission, has a series of very, very, very bright point-like sources, as well as a lot of diffuse emission coming from the center. So what exactly is this bright X-ray source at the center of Andromeda galaxy? What is it? Well, we may very well ask the same thing. What's at the heart of the Milky Way? And this is there's a laser tracking, an artificial star created by an observatory down at the VLT, by the European Southern Observatory. Interesting photos taken by people under the deep night sky. And that laser is pointed at the sky to make an artificial star, to use adaptive optics, so you can actually look at the deepest, deepest, deepest center of the Milky Way. So adaptive optics is critical for doing that, and that's what we talked about in a much, much, much earlier episode, and that allows us to to get a better view of something obscured by clouds. All right, so remember that dust is blocking completely our optical view of the center of the Milky Way. So we have to use infrared or radio observations or X-ray observations in order to see what's happening down in the center of the Milky Way. Because we can see the center of the Andromeda galaxy because it's open and facing to us. It's just millions of light years away, so that doesn't count. We want to see what's in our backyard. Well, if we combine a series of observatory images of a large area of the sky using NASA's great observatories, specifically the Spitzer Infrared Telescope, the Hubble in the near infrared, meaning just a little bit longer than the red, about 10,000 angstroms or so, and the Chandra X-ray Observatory, we combine these together and we see an incredibly turbulent area in the downtown central area of the Milky Way itself. There's lots of shredded gas and huge star formation and X-ray emission and dust and gas all careening about. So it's a turbulent, violent downtown area. But let's see what we can determine what the heck is actually going on there. If we look specifically in X-rays by the Chandra X-ray Observatory and do look at the inner 400 by 900 light years, we see there's a huge number of X-ray point sources, and these are likely neutron stars and black holes. But there's also dead center some very, very diffuse, large, bright X-ray sources. Especially one, the most intense, is actually towards the center. And that's really what we're going to be looking for. We can actually then also look at the same rough size scale, but tilted at an angle, in 90 centimeter, almost meter long wavelengths in radio emission. And we also see extraordinarily bright things happening. We also see circular, spherical features as well. Those are radio lobes due to expanding gases from supernovae. We also see kind of snake-like structures that are very similar to prominences around the sun, except they extend many, 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 many light years. Now, if we then zoom in even more with higher resolution using the Chandra X-ray Observatory, the inner 100 by 100 light years, we see diffuse X-ray emission, but it gets brighter and brighter towards the center. There's even more point sources from neutron stars and black holes that are towards the center. But it's again that incredibly hot diffuse gas that is millions of Kelvin that somehow is being heated to extraordinary temperatures close to the center of the Milky Way. And this shows it again that where Sagittarius A star is actually the center where this bright radio emission is coming from that we saw in the other image. So this X-ray emission is in diffuse cloud forms as well as lots of point-like sources. And those cloudy forms are superheated gas that's been heated to millions of degrees and is emitting X-rays. And the inner region has a lot of very interesting bits. There are non-thermal filaments and radio arcs, and the radio image shows that there's an enormous magnetic field that's causing electrons and protons to spiral at very high speed, nearly the speed of light, through these magnetic fields, causing these filamentary structures. There's also supernova remnants labeled S and R. And those supernova remnants are the result of an exploded star. But there seems to be a large number of them. So for some bizarre reason, there's lots of supernovae happening in there. And the dimensional scale is about 1,000 light years across that dashed line from upper left to lower right. In any event, we can zoom in radio views. We can take the VLA image, we can zoom in further and look at closer and closer and closer. And as we zoom into these closer and closer images, we see finer and finer details of radio disruption. But each of these is a different wavelength. That's the real trick, is we can't do this with the same wavelength, because you get different resolutions at different wavelengths. So we have to actually change our wavelength of observation in order to zoom in closer and closer, with the last one being the shortest wavelength as infrared. So this is another radio image, also VLA, that demonstrates that there's enormous radio arcs, which are the magnetic field of that region accelerating material and having synchrotron emission, meaning that brightness that looks like an arc is a result of electrons spiraling at nearly the speed of light in a very strong magnetic field, and as they do so, they emit radio light. And there it is again, another radio arc image, just to show you that, and it looks very interesting. It has a wispy sort of structure as the magnetic field spans hundreds of light years out from the center. But we have that bright source that's deep in the center, and what exactly is going on deep in the center? Well, let's take a look even closer. At about 3.6 centimeter radio light, the inner 20 by 20 light years shows gaseous material that is actually spiraling around at extraordinary speeds, hundreds of kilometers per second, or thousands of kilometers per second, yet there's still an incredibly bright point source right at the center. And there's these arms of gas that are swirling around, but look at that bright source. And we're going to go zoom in even further at 3.6 centimeters, and zooming in further we see the arms of gas that are moving extraordinarily fast, but yet there's still that incredibly bright point source right at the center. What is going on there? Well, this was a result of a massive study by Andrea Getz, who I've put in the picture in the lower left-hand frame. She heads up a group called the Galactic Center Group at UCLA, and they went and used the Keck Observatory in adaptive optics mode in order to actually visualize the center of the Milky Way in the near infrared. And we can see the difference in the Keck Observatory with adaptive optics on and adaptive optics off. And we can definitely see that you get much higher resolution with adaptive optics on. And the plus is the center of the dynamic structure of all of these stars now. All of these objects are stars that you see that are orbiting something down in there. We see an incredible number of stars inside the center of the Milky Way. So in the inner 2 light years by 2 light years, this is one of the Getz group's images, these in infrared, we see that there's thousands of stars inside of a volume of space where nearby the sun there's only like 2 or 3 stars, because even you'd have to go diagonally across this image to get from the sun to Alpha Centauri. That's out by us, but down in the center of the Milky Way, there are literally thousands of stars packed into the inner 2 light years around the dynamic center of all of this. But yet there is no distinct bright object directly in the center. There's some bright gas and bright dust that's being warmed. There's some bright star-like structures, but there's nothing directly bright deep in the center in infrared. So now what we can do is, this is what Getz's group has been doing for the last 20 years, last 2 decades. She's been leading a team at UCLA, and it's called the Getz Group, and it's the Galactic Center Study Group, and they've been actually mapping using the Keck Observatory and other observatories in order to discover the actual motions of the stars down in the center. And what we see is that these things are swirling about over the course of about 15 or 20 years. And in order for them to move in this exact way, according to Newton's law of gravity, the thing that's down there must be 4 million times the mass of the sun in order for them to move that fast over the size scales that we're looking, which correspond to huge orbital parameters. And so there's something big there. And this is a map of the thing that we actually saw in the previous little video that they made. So here's her work with her team at the UCLA. And we see one of the more important ones is that the star SO2, which kind of has which is that reddish pinkish ellipse in the dead center that's very, very small. That one has an orbital period of about 20 years, and so every 20 years it gets close to whatever is at the center. And they can actually map these things and see and they can actually track the motions. So here's another interesting bit of work that they've done, and what's incredibly important is what is going to happen in zooming in just a little bit. So now as it's zoomed in, we can see a specific star that's actually moving around. I'm sorry, this might be the Max Planck Institute's work instead. We'll be actually seeing some of their work as well. So there's another star, there's that one that kind of whips around really tight, and that has a 20-year orbit. So they're going to zoom in on the box, and the box is going to zoom in, and we see it's tracing out the orbit of one star going around that plus, and that plus is the dynamic center of the Milky Way. And in order for that star to move that way, something's got to be 4 million times the mass of the sun, according to Kepler's laws. Now, what's amazing is that starting July of 2018 is that Andrea Getz's group, after 20 years of studying this has been her career, is that they're finally waiting for this star, S0 number 2, to pass within 1,000 times the size of whatever this thing is, and I've just given it away. There's a supermassive black hole at the center of the Milky Way, and what they do is they're actually checking to see how its orbit changes, and there are predictions as to what the orbital appearance will be if gravity is governed by Newton's laws or if it's governed by Einstein's theory of general relativity. And they're completely different, and they can actually have such an accurate degree of measurement that they can actually tell between the two theories. They can tell because the orbit will have a different shape. The speeds will be different. They'll accelerate and decelerate differently there. And so you can actually distinguish between the two. And in September of 2018, they're going to issue forth an interesting thing where it discusses exactly how this thing has changed. So they made their May observations, they made their April observation, and now as it's leaving the gravity well, being so close to that supermassive black hole, that they're going to be able to they're going to be able to tell something important about the nature of space-time close to a supermassive black hole. So watch for the future, and this comes from their website. Just go to the UCLA Galactic Center Group with Andrea Getz, G-H-E-Z. All right, so this is also a study by the Max Planck Institute, led by Dr. Genzel, and they assume that something is about 3.7 or 4 million solar masses. Let's just call it 4 because what the heck. And we can see that this is the orbit of that particular star. The dimension of this orbit is a few light days. So this thing is going around in 20 years where, remember that the Voyager spacecraft, if we look at how far Voyager is currently from the sun, it's about 17 or 18 light hours, almost a light day away. So about 1/8 of the length of the long axis of this ellipse that you see here is about how far the Voyager has gone from the Earth. But the Voyager has taken since 1975 to get there, taken 40 years to get there. This makes one of those orbits and goes way out past that and comes back 8 times the current distance between the Earth and Voyager, which is at 100 astronomical units. So it would be 1,000 astronomical units away. So this is a very long orbit, but it does that orbit instead of taking hundreds or thousands of years to do, it takes 20. So something's yanking on it really hard, and that something is a supermassive black hole at the center of the Milky Way. That's about 4 million solar masses. And this is what they found in 1992 to 2013. Their observations could be modeled by general relativity, which is the curve on the right-hand side. So the orbit is what's been done. The UCLA group by Andrea Getz is in the red star pluses, and the Max Planck group is in the blue. But what we see is that both of them can fit the general relativistic group, but now they're actually going to measure the acceleration deceleration over the course of the next few weeks and months as it passes by the supermassive black hole named Sagittarius A star, or SGR A star. All right, so here's what those orbits kind of look like, and we can definitely see it's kind of a nifty little view. The nice thing about the star SO2 is that the orbit itself is almost face on. See, there's other stars, say SO3, or that other one that kind of swoops in on that really tight orbit in the green line. That its orbit is not so face-on, and we can't see a full orbit. However, SO2 is almost a face-on ellipse, and its orientation is perfect for actually making these kinds of measurements and knowing the mass, because we can see the exact size of the ellipse. The orientation can be easily derived because the offset of the center from the focus, from the apparent appearance of it. So Andrea Getz's group can make a very accurate measurement of the exact size of it, and so as well as the Max Planck group, and this is what they've been doing for the last 20 plus years. All right, so what we've learned over the course of time, and it's really a fascinating thing, is that stars are moving very quickly near something that is not making any light. There's an enormous amount of radio emission, but still it's not visible. There's no visible object. There's no bright star. And there's nothing, if there was a 4 million solar mass star there, or 4 million solar mass cluster of stars, it'd be pretty bright. It'd be insanely bright. And it's not there. We see a bunch of stars in downtown central galactic center, but we do not see one bright object that overwhelms everything. So there's something there that weighs 4 million solar masses that emits almost no light but affects its surroundings amazingly. And that thing is a supermassive black hole. And we talked about black holes previously, but this is the source of all of that very interesting phenomena. The stars moving very quickly, the magnetic fields, the X-ray emission, the diffuse X-ray emission, all the cloudy structure and the violent structure is due to this thing that's actually physically really small, but has an enormous influence on its surroundings in the area. So the Galactic Center has a stellar density. There's more stars in there, millions of times more stars nearer in the volume than there are near the Earth. There's an enormous ring of molecular gas, about 400 parsecs across, that emits in radio light as well as infrared. There are incredibly strong magnetic fields that permeate the entire area. There's a huge rotating ring of gas and dust that can be seen that's a few parsecs across right around the center, and there's an incredibly strong X-ray source in the center. That means that there's a supermassive black hole in the center of our Milky Way, and that's about 3.7 solar masses. But what we saw at the outset was something in the center of Andromeda. And the Andromeda galaxy appears to have a supermassive black hole that's 100 million solar masses. This is really an amazing thing. So these are what's astonishing is that There are many ways to look for supermassive black holes, or just black holes in general, but one of the best pieces of evidence for the existence of a black hole, or even that they exist at all, is in the center of the Milky Way. And we can look for Cygnus X1, we can look for lots of other things, but just the fact that we can actually see so much detail on this object that's very, very, very close by comparison allows us to really understand the nature of black holes and general activity in our own backyard. All right, so we'll be getting, now that we've seen that, we're going to venture out into the rest of the cosmos and see what the rest other galaxies look like, and that's what will be coming up next. So we'll see you soon.